Mani Anand Aravind from F.C. Roderick Institute of Technology, Vashi, New Mumbai. He completed his PhD from Indian Institute of Technology, Roorkee in 2020. He is working as assistant professor in Electronics and Telecommunication Engineering Department. He has published several research articles in conferences and journals. His prime research interest is quantum computing. We welcome you, sir, and request you to start the session.
Thank you, ma'am. I'm very much thankful to the entire organizing committee for inviting me to deliver this invited talk. A special thanks to Dr. Payal, who took a lot of efforts to get this work done, because I was in continuous touch with her for this particular talk. Okay, the summer school is already started. Participants would have exposed most of the things of the quantum computing. I will take the participants today in a different direction today in terms of the quantum computing. Before I could start, let me make my presentation in full screen mode.
Yes.
Yeah, is it visible, ma'am?
Yes, sir.
Yeah. The topic of my talk is applications of quantum computing. I will talk about in brief of the application of the quantum computing, but I will take you into the direction of why the physical implementation of quantum computing is most important at the moment, as we know that quantum computing is one of the emerging areas like AI, ML, and like also electric vehicles. All these are very emerging topics. Along with that, quantum computing also an emerging topic, but not that much got exposure in our country, India, though in outside countries, it is highly exposed. But the important thing about the quantum computing, which is quite unnoticed, is its physical realization or physical implementation. At the algorithm level, at the architecture level, or at the coding level, many things are going on in the quantum computing direction, but less work is on the physical realization or physical implementation of the quantum computing. Now, as I said, the summer school is already started from the 25th of July. So most of the sessions would have covered the different aspects of the quantum computing, like what is quantum computing, why it is important, how it is applicable, what are the different aspects of the quantum computing, what is the difference between quantum information and quantum computing, and how this quantum computing can play an important role in different areas in the coming future. Nowadays, we talk about this big data analytics, then cloud computing, all those things. We need to think about the can the quantum computing contribute in these areas also, right? So before I could start with my presentation, I would like to introduce you all with the presentation outline. I will be talking about introduction. In that introduction, I will talking about history of computing and why there is a need of quantum computing. What will happen if you don't think of the quantum computing, that we will also discuss. Then, as I said, that summer school is already started. Many experts would have spoken about the quantum computing. So I will speak in brief on quantum computing. That is, what is a Turing machine? What are the different principles of quantum mechanics and why they are needed? Then what is the fundamental unit of the quantum computing, that is qubit? Then what are these quantum gates and quantum circuits and quantum algorithms also? That I will discuss under the umbrella of quantum computing. Then the most important topic, which was given to me, is the applications of quantum computing. Again, I will talk in brief as there is a time limit. I will talk about how the quantum computing will play an important role in the healthcare sector. Then, in case of civil engineering, how can we utilize the quantum computing for the truss optimization? I will talk about the truss, what the truss is in case of the civil engineering. Then in case of electrical engineering, how this quantum computing can play an important role in deciding the power flow in a complex electrical network. That we will also talk about. Now the question comes, how the quantum computing is to be implemented. As I said, that a lot work is done on the algorithm level in the quantum computing, and less attention is given to the physical implementation of the quantum computing. In that, I will talk about DiVincenzo's criteria, why this criteria has to be followed for the physical realization of the quantum computing. Then I will talk about different types of realizations for the quantum computing, and I will take you through the one of the physical realizations of the quantum computing through the one of the novel areas, emerging areas in VLSI industry, which is called as Spintronics, spin electronics. How the spin electronics can be utilized, or spin of electron can be utilized for the realization of the quantum computing. Then I will talk about what work we had done during my research at IIT Roorkee. That is how we achieved different, what we can say, different tasks. So the task was transmission coefficient modeling of spin-torque-based qubit architecture. Then how the quantum computing can be utilized for the realization of reversible Boolean computing. I will talk about this reversible Boolean computing, which is an emerging area. Then we will talk about the spin-torque-based reversible D-latch. All of us are familiar. Those who are from the electronics and computer background, they must be knowing what this D-latch is. But some of you may be knowing what is this reversible D-latch. That again comes for the computing also. Last but not least, I will be talking about quantum Fourier transform. All of us would have heard about quantum Fourier transform, but less would have heard about quantum Fourier transform and why it is necessary, why this quantum Fourier transform is very, very important from the perspective of realization of this quantum Fourier transform in terms of the quantum computing, followed by the conclusion. So that will be the outline of my entire presentation. I will try to accommodate it in 1.5 hours. Probably it would finish earlier, probably it will take some more time. So be patient. Right. When we talk about the computing, we need to look back and see in literature what is the history of computing. When we talk about the computing, we talk at the computer level or algorithm level or the coding level or at the software level. But again, at the realization level, there have been 4 generations. The first generation was started in 1951 and lasted till 1959. What was in that during that period? Why it is called 4 generation computers? Because the computers which were developed during that era, during that period, had 5,000 vacuum tubes, approximately 5,600 vacuum tubes. It had crystal dials of around 18,000. It required 300 relays, and bit rate, means at the rate at which data is supposed to be transferred, was only 2.25 megahertz. And storage, can you imagine what was the storage capacity? The storage capacity was only 1,000 words, but it was the beginning. Like for the quantum computing, present days are the beginning. So that kind of a thing was for the first generation computers. It was very difficult. Just look at that picture. If you look at it carefully, it is occupying the entire room to get it done, or to entire room for the computation purpose. Then there was a entire revolution due to the invention of the transistor at the Bell laboratory. The transistor changed. Because of the transistor, there was a paradigmic shift in the computing. The size was reduced from a room to a small, on the fingertip, I can say. The transistor developed at the Bell laboratory. Why they were so special? There were so many reasons. First reason was they were reliable, unlike vacuum tubes. Second, because of the utilization of the transistor, there was an increased computational speed. Then, as I said, that the transistors are available on the fingertip. We can say that there is a reduction and drastic reduction in volume and cost because of the utilization of the transistor for the computing. And because of that, we can see nowadays the information technologies. Why? Because they are affordable. The computers are affordable. Personal computers are affordable. A common man can purchase. Earlier, it was not like that. The computers were very costly because of the invention of the transistor and evolution of this transistor due to the Moore's law. Over the years, the computers have been cheaper. And the most important thing is less power consumption. Day by day, we are observing the computers are taking less power because of the increase in integration density. That was the second generation, which was during 1959 to 1964. Again, we moved from the second generation to the third generation. What was the interesting thing about the third generation? Integrated circuits, circuits on the chip. Why integrate? That is called the ICs, right? It started in 1965, 64 rather, and ended in 1971 before the fourth generation is supposed to be started. So what was the speciality of this third generation? The speciality of the third generation was, as integrated circuits or ICs came into the picture, they were more reliable. In comparison to the discrete transistors, they were very cheap. Utilization of the microprocessors, microcomputers, and mini computers. Again, it was a very big revolution. Then we moved from the third generation to the fourth generation. That is 1971 till today. Single silicon chip. We talk about single silicon chip. And what are the different features of this single silicon chip is VLSI, circuit packaging, and memory chips development. So these are some of the important features of the fourth generation. Now the question is, why to move from this fourth generation to something like quantum computing? Why there is a need of quantum computing? As far as we have gone through all four generations, the reason is that now the semiconductor industry are struggling to follow the Moore's law. Now the question comes, what is this Moore's law? Moore's law is, Moore has stated that for every 18 months, the number of transistors on a chip gets doubled. But why it is struggling nowadays? It is struggling nowadays, the reason is channel length of the transistor. Now, channel length of transistor is in the order of nanometers, and now it has become very difficult to reduce it further due to the quantum effects, due to the channel length modulation, due to the reduction in channel length. Because of that only, it has become very, very difficult, or rather we can say that semiconductor industry is struggling to follow the Moore's law to double the transistors on the chip every 18 months. Because of that only, we need to think of something which could replace, I should not say replace, which could be an option for the conventional computing by saying that quantum computing. Why? Because when we talk about the conventional computing, we only talk about the realization to the transistors, right? That's why you can say that now there is an integration density limitation. Let us suppose that in future, the channel length becomes size of the atom. All of us know what is the size of the atom? 1 angstrom. If it becomes 1 angstrom, beyond that we cannot think, and there could be a stop to the integration density. Therefore, we need to search today itself for the options which could, with the help of which we could get the solution, or we could get rid of these kind of obstacles. So this is what the integration density limitation in classical computing architecture. The second is the power dissipation in reversible Boolean logic based circuits or computing. When we talk about the classical, let it be anything. Even we are in the era of this big data analytics and AI and machine learning. And nowadays, everything we do through the websites, huge data. When we talk about basically what the data is 0 and 1. 0 and 1 means representing the switches. So huge data means so much of switching. When a data is moved from 0 to 1 or switched from 0 to 1, there is a dissipation of energy. When we talk about large circuits, when we talk about huge data computing, we need to talk about the power or energy dissipation. So that power and energy dissipation is used in irreversible Boolean logic circuits. Now we need to understand what we mean by, all of us have understood Boolean circuits. All of us have understood the Boolean logic. But have we understood what is the difference between a irreversible Boolean logic and reversible Boolean logic? Let us take an example of a NOT gate. What a NOT gate does, for 0 it provides 1, for 0 input it provides 1, and for 1 input it provides 0, right? So but if you look at the NOT gate, all of us know that just by looking at the output, we will be able to know what was the input. But the same case is not applicable with other remaining gates. Take the example of AND gate, take the example of OR gate, take the example of XOR gate, even take the example of more complex gate that is full adder or half adder. The moment you see the output, you lose the information that what was at the input. For example, take the AND gate. There are 4 possible combinations of the AND gate: 0, 0, 0, 1, 1, 0, and 1, 1. So we get 1 at the output when both are 1. That we know. If 1, we know that the at the input there were 1, 1. What if for the remaining 3 combinations, that is 0, 0, 0, 1, and 1, 0? For all these 3 combinations of the inputs, you always get 0. So just by looking at output, you never know what you can just predict that out of these 3 there must be 1, but you cannot exactly decide what was at the input, and that is what the information loss. That is what called the irreversible Boolean computing. So we need to move from irreversible Boolean computing to the reversible Boolean computing. Many people have done this reversible computing with the help of the transistors, but that is not the correct way. The reason is transistor itself dissipates the energy through the switching. That is not the quantum way. That is a classical way of switching from 0 to 1 or 1 to 0. Other than that, there is one more problem. What is that problem? The classical computing could not solve complex problems efficiently. Which complex problems it cannot solve efficiently? The number one is number factoring. It is always easy to multiply 2 numbers. For example, 4 into 5, that is 20, or 5 into 4, that is 20, or 3 into 2, that is 6. But how difficult it for the computer, as computer is not an intelligent device. How it is difficult for the computer to factor a number, say 5 or say 6. How to factor it into 3 into 2? That is very, very difficult for the classical computing to carry out efficiently. The second example is data searching from the unordered list. That is also a difficult thing for the classical computing. So to get rid of such obstacles, we need to move from the classical computing to the quantum computing. That's what the reason is why there is a need of quantum computing. Now, when we talk about the quantum computing, the basic machine is the Turing machine. What is this Turing machine? Turing machine is a simple magnetic tape. It has 3 things. One is 0, or the data is supposed to be stored in 3 forms: 0, 1, and blank. Right? In the previous days, we would have heard of magnetic tapes having the heads, and with the help of those heads, we will be able to read or write the data on those magnetic tapes. So any complex algorithm can run on the Turing machine with the help of the program and finite state control. Now, at the beginning of this Turing machine, there are some blocks on the tape are blank at the start. Now, what this Turing machine does, it processes symbols 0, 1, and blank. Right? Now, what this head does, all of us are familiar with. If you have seen the magnetic cassette recorders or cassette players, you would be aware of this magnetic tape or Turing machine. What this head does, it follows the program instructions, whether to write, whether to read, or keep it blank, erase or move tape. All these things are done by the head. So this Turing machine plays an important role in case of quantum computing. Now, when we talk about the quantum computing, we need to know how this quantum computing behaves, how it operates. Now, as far as classical computing is concerned, we follow the classical laws, right? But as far as quantum computing is concerned, it has to follow the principles of quantum mechanics, right? Some of you being a computer engineer is quite difficult to digest that. What is this principle of quantum mechanics? Let us go through quickly the postulates of quantum mechanics. For a quantum mechanics, the first postulate is a physical system is described by the state space of the system. So it will have a state space, right? And time evolution, how the system will be evolved, that is governed by the Schrodinger equation. You would have heard of the word Schrodinger cat. You can go through it in detail and to understand what is this Schrodinger equation and how this Schrodinger equation governs the quantum mechanics, right? If you look at this equation, I have presented this equation. There is a Kate notation. There are 2 notations in quantum computing. Bra notation and Kate notation. We are using the Kate notation for this Schrodinger equation. There are two constants in the Schrodinger equation. One is a Planck constant, another one is the Hamiltonian operator. This capital H is the Hamiltonian operator, and this small h is Planck's constant. All of us are familiar with those who have studied the physics, they all are familiar with this Planck constant, and its value is 6.62 into 10 raised to power of minus 34 joules per hertz. Right? So the evolution of the system is supposed to be governed by this Schrodinger equation. Right? Now, the most important thing is the measurement in quantum computing. Right? So we can say that for a quantum system with a set of m possible outputs or inputs also, if you look from the output towards the input, the state measurement is described by a collection of measurement operators. And these measurement operators are linear and act on the state space of the system. This is the third postulate. The fourth postulate is, as I said, that the physical system is described by the state space of the system in mathematical terms. We need to understand what the state space is. The state space is nothing but tensor product of two vectors. Now I have shown the tensor product here. I have shown the tensor product here. If you look at this tensor product, it is like a matrix multiplication. I have given you the one example here. I'm showing you. Just use the pointer here. Just look at it. Two matrices are multiplied. Tensor product of two matrices are achieved there. A, B, C, D. First matrix is tensor product with the E, F, G, H. In a normal matrix multiplication, what we do, we simply multiply A into E, then A into G. But in case of tensor products, we don't like this. We multiply first parameter of first matrix with the entire second matrix. And we follow the same thing for the remaining parameter or remaining second matrix. The remaining parameters of the first matrix multiplied with the second matrix. So that will expand the size of the matrix from 2 by 2 to 4 by 4. So this is what the basic difference between a tensor product and a matrix multiplication. So these are the sum of the postulates. Now let us talk about the qubit. Qubit is the fundamental unit of quantum computing. We cannot think about the quantum computing without the qubit. Let us try to understand this qubit by comparing it with the simple bit. What is a bit? Bit is a kind of a switch. What it does, it provides us the information 0 or 1. When the switch is closed, the information is 1 or it's up to you which logic you are using. Either it is 0 or 1. So exactly opposite. 0 and 1 never meet each other. Right? As far as physically representation, okay. Now what is this qubit? Qubit is a quantum state. It is neither 0 nor 1. Right? It is a quantum 0 or quantum 1. Unless and until you measure it, it is in the quantum state. Right? So what such kind of examples which can describe a qubit? Photon polarization state, two energy levels of electron. Electron moves from a lower orbit to the higher orbit or higher orbit to the lower orbit. That is also possible. And the most important thing is the electron spin, through which I am going to take you through this entire presentation. As far as a qubit is concerned, it is a vector quantity. It needs both magnitude as well as how it is oriented. What is its direction? Whether it's upward, downward, left, right, in which direction it is. Is it an entangled state? I will come across this entangled state. Is it in a superposition state? What kind of a state it is? That's why it is a vector quantity. And these qubits are evolved on the blast with the help of the blast sphere. How we represent the bits, they are either 0 or 1. But as I said that there are infinite number of combinations of these zeros and 1. Therefore, they have to be represented on the blast sphere with the help of vector. Such kind of a thing you would have seen in electromagnetics engineering, but the same sphere can be utilized in case of the quantum computing with the help of the vector. Now vector is or we can say that the qubit can be represented by a vector with an angle phi and theta. We are familiar with this phi and theta. Phi is in the xy plane, theta is along the z axis. Now, as I said that 0 and 1, they are quantum 0 and quantum 1. How to represent them mathematically? 1 0 transpose or 0 1 transpose. Therefore, we can say that the qubits exist in superposition or linear combination of the states. Right? Let us move forward. Now, as I said that, as I have already explained what is a qubit is, now let us talk about quantum gates. We are already familiar with the Boolean gates like NOT gate, NOR gate, NAND gate, OR gate, AND gate, all these gates we have seen. But we haven't heard about quantum gates. Just now I have explained the difference between reversibility and irreversibility, right? As I said that except NOT gate, all other classical gates are irreversible. But when we talk about the quantum gates, all of them are reversible. All of them are reversible, right? So some of the quantum gates I'm presenting here through their matrix representation. There are polygates, rotation around x-axis, rotation around y-axis, rotation around z-axis of a particular vector or a qubit are represented by the polygate. So their matrix representation is shown here. It is not like a unit matrix. Try to understand the difference between unit matrix and polymatrices. 0 1 1 0 0 minus I 0 1 0 0 minus I. Then is identity gate or that unit matrix. The NOT gate is represented as 0 1 or 1 0. That is rotation around the x-axis. Then the phase shift gate, the magnitude will not be changed, only phase will be changed. The most important gate in quantum computing other than the C0 gate, I'm coming to that C0 gate, that is control NOT gate, is the Hadamard gate. This Hadamard gate is the constituent of many more quantum circuits. Even we cannot think about the quantum circuit without the Hadamard gate. This gate is very, very important. What this gate does, it changes the axis of rotation from x-axis to z-axis or z-axis to x-axis, but it plays a crucial role in designing the quantum circuits.
Yes. So can you just explain the difference between the Hadamard gate and the previous one, phase shift gate?
Yeah. The phase shift gate is only for the change in the phase. It doesn't change the magnitude, only there is a change in the phase shift. As far as Hadamard gate is concerned, for this Hadamard gate, we use this Hadamard gate for the change of rotation of axis. Let us suppose that the state of a qubit is along the z-axis. If I rotate it, if I want to change this axis of rotation, I will use the Hadamard gate and I will move it from the around the z-axis to the around the x-axis. Hadamard gate's function is only to change the axis of rotation. And the best example of the Hadamard gate is, or the modified version of the Hadamard gate is 3 qubit quantum Fourier transform. We use the quantum Fourier transform for the similar thing directly with the help of 3 qubits or 5 qubits or 7 qubits or so on. Got the difference, ma'am? Hello?
Yes, sir. Yes.
Shall I move forward?
Yes, sure.
Yeah. So let us talk about 2 qubit gates. Now, as I said that C0 gate, it is the, what we can say, it is the most important building block of the quantum circuits. If you find any quantum circuit, you will not see that quantum circuit without the utilization of controlled NOT gate. It is very, very important, right? Now, what this C0 gate does, if you look at this C0, now, as I said that all quantum gates are reversible in nature. No quantum gate is there which is irreversible in nature. So is the C0 gate. If you look at this C0 gate, it has 2 inputs and 2 outputs. The inputs are A and B, and outputs are A and A Kronecker product B, or A XOR B, we can say. What does it mean? There will be change in state of B when and only when the A is 1. A is quantum 1, not 1. I should not say 1. It will be wrong. right? It should be in constant quantum state 1. If the quantum state of A is 1, then and then only B will flip its state. If B is quantum 0, it will become quantum 1. If B is quantum 1, it will become quantum 0. If you look at the output side, as I already said, the output side has again two outputs. One is the same A appears at A, right? And second one is A XOR B. Now someone may ask a question. This is utter nonsense thing. In case of the classical computing, if we take an extra wire to know what is A state, that is not the quantum way, that is a classical way. It has to develop the A in an inherent way through the system without using any external wire, right? So that is what the speciality of the C0 gate. So with the help of this C0 gate, we will be able to control the state of a second qubit if the state of the first qubit is 1, right? Matrix representation is there. Then second two qubit gate is controlled unitary gate. What is this control unitary gate? If A is 1, then there will be specified operation specified as U on the qubit B. If A is 0, nothing will happen. The same B will be passed to the output, right? So this is the difference between C0 gate and control U gate, right? Shall I move forward? Okay. Next is the Toffoli gate. This is the name of the scientist. Actually, gate is the control NOT gate. Now, this is the modified version of the C0 gate. Now, what is the difference between C0 gate and Toffoli gate or CC0 gate? That we need to understand. If you look at the input, there are three inputs, A1, A2, and B. If you look at the output, there are three outputs, A1, A2, and some function. I will not talk about this function because it will take so much of time. If A1 and A2 both are in quantum state 1, that we both are 1, 1, then only B will be flipped. Or if B is 0, it will become 1. If B is 1, it will become 0. Right? So we can say that this is the modified version of the C0 gate. Right? So for what purpose we use these universal Toffoli gates? The reversible computations are performed by universal Toffoli gates. Other than that, 2 qubit quantum gates can be used to implement the Toffoli gate. If you look at the quantum circuit given exactly below in the slide, it has 3 states, but the entire Toffoli gate, which looks like a single operation, it's quite difficult to achieve the single operation in quantum computing as far as physical realization is concerned. So you have to decompose the single operation into two qubit based operation. So if you look at the quantum circuit given at the bottom of this slide, so at the input state, 3 states are there, at output state, 3 states are there. There are 6 different C0 gates are utilized to realize the Toffoli gate, and different 2 Hadamard gates are also utilized, and different gates are utilized, whether to rotate them around the x-axis or y-axis or z-axis, right? So as far as this particular decomposition is concerned, we can see that 6 different C0 gates, 2 Hadamard gates, and remaining are single qubit operations. So we can say that 3 qubit Toffoli gate or CC0 gate is a decomposed. Very rarely people work on this decomposition kind of a thing. They work at the algorithm level, but very rare people work on this kind of a thing, right? So this is a decomposition of this Toffoli gate, which can be carried out with the help of the C0 gates and single qubit operations. Now, I have already explained this reversibility and irreversibility, but when we look at it at the transistor level, at the physical realization of the things, every transistor dissipates. Why I am talking about the transistor? Because transistor is a device to represent a 1 bit of information, 0 or 1. When we switch the transistor, it changes from 0 or 1 to 0, right? But during this transition, there is a loss of information, not loss of information, there is a heat dissipation. Or every bit loss of information, there is a heat dissipation. Now, how much this heat dissipation? This heat dissipation is kT natural log 2. What this kT? KT is a Boltzmann constant. Its value is 1.38 into 10 raised to the power of minus 20. I am not going into the details of the units, it will take time. T is the temperature of the external environment. This is very, very important. In which environment you are carrying out this information transition, and this E is energy consumption, that is per bit loss of information, right? As I said, that K is a Boltzmann constant. Now this is not a single bit of information. Let us imagine now we are in the information age, information technology is, there is a huge data manipulation. So how many switching activities, or how many, what we can say that operations are going on, which results in the huge dissipation of the energy, right? And why? Because of the, it is carried out in a classical way, right? So we can say that there is a high information loss as it is irreversible in complex irreversible circuits. And as I said in the beginning itself, Boolean gates are irreversible except NOT gate. And one more important thing as far as quantum computing is concerned, quantum computing does not lose information until it is measured. So the quantum measurement process, why? That needs some expertise to explain. Quantum gate measurement process is irreversible. The moment you measure the quantum state, it loses entire information and it converts the quantum information into classical information. So these are the some of the aspects of the reversibility and irreversibility. Now let us talk about the quantum circuit. Now we have spoken about the quantum qubits, then quantum gates. Now let us talk about the quantum circuits. What is a quantum circuit? Sequence of gates, right? Single qubit gates or 2 qubit gates or 3 qubit gates to carry out a desired operation, right? We can say that a quantum circuit is the structure of unitary operations and measurements on a n qubit state, right? If you look at this quantum circuit carefully, it has multiple input states, multiple output states, and different multiple state operations, QA, unitary operations, UA, UB, UC, UD. This can be carried out with the help of the single operations like Z operation or H operation. That is one of the single qubit gates to carry out a particular operation when qubit is required to be rotated around the Z axis. Then what is the difference between a quantum circuit and a quantum algorithm? A quantum algorithm is a stage-by-stage process where each edge of the stage can be executed through a circuit. It is a stage-by-stage process, and each stage has to be executed by a quantum circuit, right? Then let us talk about, in brief, Shor's algorithm. As I said, that it is quite difficult for the classical computing to take care of this complex tasks like number factoring or searching formless database or an unordered list. Quite difficult. So these things are addressed by two scientists. One is a Shor, second one is a Grover. What Shor addressed, how efficiently we can obtain the number factoring with the help of the quantum computing. And what did Grover did? I have given you for the information purpose, I have given you the references at the bottom of the slide. You can go through those references. And Grover has given searching formless database or an unordered list, right? Let us move forward. Now we have spoken in brief, not in detail, on the quantum computing. But the question comes to our mind: why we are studying the quantum computing? Is there any application of the quantum computing, or only we are talking virtually, not actually? What is the quantum computing? When we talk about any system, any technology, or any invention, or any new thing, what we look at first, at its applications. Right? When we talk about the quantum computing, as I said in the beginning itself, we can use the quantum computing for the healthcare. Now, one may ask a question: how can we use the quantum computing for the healthcare? To accelerate the diagnosis. It's quite difficult for us to accelerate or to diagnose a particular disease with the help of in a classical way, right? So quantum computing, because quantum computing has the ability to access the patterns quickly. Therefore, it can accelerate the diagnosis, personalizing the medicines, and optimizing the pricing. These things can be done with the help of the quantum computing. Also, in case of machine learning algorithms are particularly relevant to the healthcare sector, which are obviously quantum enhanced. So this could come under the umbrella of quantum machine learning. Now, as I said, three key potential quantum use cases are there for the healthcare industry. That is, first, diagnostic assistance. It provides diagnostic assistance. How it provides diagnostic assistance? Diagnose the patient early. How nice it is if the disease is diagnosed early, we can cure it accurately and efficiently. The second use case is the precision medicine. What is this precision medicine? Keep people healthy based on personalized interventions or treatments. Right? This is a very, very important precision medicine. And third is the pricing. Optimize insurance premiums and pricing. So this way we can utilize the quantum computing in healthcare sector. The next thing is, now let us continue with it, not next thing. Now, as I said that it revolves around three things: pricing, diagnostic assistance, and precision medicine. These all are interrelated with each other. So what will happen if there is an accurate diagnosis? It enables precise treatments as well as better reflection of patient risks in pricing models. Also, the quantum computing has the potential to improve the analysis of medical images. As I said that they can quickly access the pattern of the images. Therefore, doctors will be able to diagnose it early, right? Such as age detection and image matching. Also, diagnosis assistance could improve health, cost, experience, and jobs, while precision medicine should enable better patient outcomes and experiences, and pricing is expected to help reduce cost. The reference is given at the bottom. Now, how it does, how the quantum computing carry out its significance in the sector of healthcare. Now, I have presented the comparison between umbrella approach to the classical way and precision-based approach with the help of the quantum computing. In case of umbrella approach, what we do, patient reported symptoms. Then we use the umbrella diagnosis and give the umbrella treatment like giving some tablets or something like that without analyzing anything. But in case of precision-based approach, we consider many factors. Based on many factors, the granular health status is prepared. And based on the granular health status, the precision interventions are given. Right? So this is what the difference, this is what the contribution of the quantum computing in case of healthcare sector. Now, as I said in the beginning, while discussing the presentation outline, I said that we will be discussing the quantum computing. We'll be discussing the quantum computing for the civil engineering also. When we talk about the civil engineering, we should not forget about the truss. All of us would have studied in first year of engineering the truss while studying the mechanics, engineering mechanics. What is a truss? Truss is an assembly of members such as beams connected by nodes that create a rigid structure. If you look at that truss carefully, it has different beams, then nodes. Now, as far as when we talk about those beams and nodes connect the different beams. But when we talk about the truss optimization, we need to talk about two things. One is the length of the beams, three things basically. Second is the strength of the beam, and third is the cross-section area of the beam. So these trusses are very, very complex and need some kind of a calculations to carry out the optimization. What should be the cross-sectional area for each beam, right? So for that purpose, we can utilize the quantum computing through the different quantum algorithms. If you look into this slide carefully, this box truss system is given. We are not going to into detail because we are not expert of this truss kind of a thing. Just I'm explaining. If you look into this truss carefully, there are different trusses connected to the different nodes. The trusses are E1, E2, E3, E4, E5, E6, E7, E8, E9. These are connected to the nodes N1, N2, N3, N4, N5, N6, and the structure is called box truss system. Second structure I have referred to one of the thesis to take this information. The second one is bridge truss system. You would have seen such kind of a truss system on the bridge. Nowadays, they are also in India. Not nowadays, long back also, right? Here also, the different beams are connected to the different nodes. Now the question is, what is the role of the quantum computing in case of Truss optimization? The role of the quantum computing is to optimize the area, cross-section area of this beam. Some beams are at bottom, some beams are at top, some beams are at the cross. So which beam will have, or which arm will have, I will use the word arm because I'm not technical expert of that. I will use the word arm. Which arm will have what cross-sectional area? Who will decide that? For that purpose, we will be using quantum computing algorithms to carry out that task. Right? So how that task is to be carried out? Just I'm giving it in brief. What is an algorithm? It is a set of instructions, right? So first they will do set up the finite element problem with a specific selection of cross-section area. Some initial they will take, right? Like an iterative process. All of us have studied Gauss method, Newton-Raphson method, all those things. Similar way is there. Classically solve the finite element problem to obtain the reverse factor for every truss. So you will calculate the reverse factor. This is a term related to the truss. Now, with the help of the quadratic unconstrained binary optimization for the optimization of truss allows a change in cross-sectional area. How much cross-sectional area is for the each arm? That will be decided by this quadratic unconstrained binary optimization. Once it is done, now solve the problem to obtain the optimal selection of the cross-sectional area. Now go to the second iteration, then go to the third iteration, and the process will go on till you get the optimized things. So in this way, we can use the quantum computing for the civil engineering. This is one of the examples, right? And go on repeating these steps 1 to 5. If oscillating results are observed, when a truss oscillates between smaller and larger choices, reduce the step size, that is the cross-section area small, until the desired accuracy is obtained. So this is a significant contribution of quantum computing in case of civil engineering also. Let us move from the civil engineering to the electrical engineering. Now one may ask a question, what is the role of quantum computing in electrical engineering? All of us know when we talk about the electrical power system, the electrical power system has three components: generation, transmission, and distribution. Forget about generation and transmission. Just talk about forget about the generation and distribution. Let us talk about the transmission. The transmission is a huge network through which we will be able to allow the flow of the power. Now, as far as the conventional methods to calculate this flow of the power is concerned, as far as flow of the power is concerned, we decide how the power will flow on the entire complex network through four things. One is the terminal voltage, which is also called as bus voltage in case of electrical engineers language. Bus voltage, or bus is a node, right, where many number of branches are connected together. Then active power, reactive power, phase angle of this bus voltage. So in terms of, we decide how the power is flowing from one bus to other bus and so on, right? So, but this will be decided, this will be analyzed, this will be designed based on the different conventional algorithms. All of us have studied in numerical methods, different methods for the, or different iterative methods. Which are those different iterative methods? The iterative methods are, first method is Gauss iterative method, second method is Gauss-Seidel method, third method is a Newton-Raphson method, fourth method is decoupled method, fifth method is fast decoupled method. With the help of these iterative methods, in case of electrical engineering, that to be in a power system, the flow of power is calculated. But as the entire system is very vast and it is not that much efficient and effective, so the question is, can we use the quantum computing to calculate this power flow in terms of terminal voltage, phase, active power, reactive power, apparent power, or phase angle, right? So if you look at this slide carefully, there is a quantum circuit shown. There are three things basically: HHL, QPU, and quantum phase estimation. So the entire quantum circuit is divided into these parts, right? Now what is this HHL? This basically it is to be represented by Haru, Hadamard, and Lloyd based quantum power flow algorithm. Right? In this, quantum Fourier transform is used. I am coming to this quantum Fourier transform. I don't know how much time I have available to explain. I will try it out. Quantum phase estimation. In this quantum phase estimation, we utilize the quantum Fourier transform. As I said, quantum Fourier transform is just like a Hadamard gate, right? Just like a Hadamard gate, to change the axis of rotation of entire 3 qubits from one axis to the other axis. But this quantum Fourier transform has so many applications. One of them is quantum phase estimation. So with the help of this quantum phase estimation and AQE is an ancilla quantum encoding. If you look at the bottom of this quantum circuit, one ancilla qubit is used. Now, you must be familiar with this ancilla qubit, as the summer school is already started since 25th. Now, you must be aware of this ancilla qubit, right? So the measurement is carried out on this ancilla qubit to know quantum power flow, right? So with the help of this, we'll be able to obtain the quantum power flow. So what will be the input? Now, it would be an iterative process. If you look at the extreme right side of this quantum circuit, there is a central processing unit. What it does, from this quantum circuit, it will take the change in voltage and change in phase angle, and based on that, it will provide change in reactive power and change in active power with respect to the voltage in an efficient way. Again, this is an iterative process. As I said, that there are several methods in case of electrical engineering to carry out the iterative process. So this is also one of the applications. Now, how this iterative process is carried out, the algorithm is given, quantum power flow algorithm. What initially we need to give to the quantum circuit, that is the phase angle, terminal voltage. These B dash and B double dashes are susceptances of the fast decoupled matrix. I'm not going into the details. This can be referred from the electrical engineering power systems. Then active power, reactive power, and the tolerance. This iterative process will be carried out till change in active power and change in reactive power is greater than tolerance value or error value. So we need to update the active power, reactive power. So in the first iteration, B dash and B double dash are given to the HHL. What is this HHL? This entire quantum circuit for the quantum power flow. Based on that, the inputs are W, change in voltage, change in power, and terminal voltage. So HHL will calculate change in phase angle and change in voltage. Similar things we do in case of classical iterative algorithms also to carry out what we can say, the power flow equations or power flow analysis. So this way also, with the help of the quantum computing's contribution, we will be able to calculate the power flow calculations in an efficient way. Now the question, as we have seen the three of the applications, first one is in healthcare, second one is in civil engineering, third one is the this electrical engineering. The question is, now we have spoken about the importance of the quantum computing, what is quantum computing. Also, we have spoken about different aspects of the quantum computing and what are the different applications of the quantum computing. The issue is, the bottleneck is, as I said in the beginning, people don't focus on physical realization of the quantum computing as they are focusing on designing the algorithms and quantum circuits. This is also equally important. Now the question is how to realize the quantum computing. Nowadays, even earlier also, people were running the quantum algorithms on the classical hardware, which is not correct. Right? Just like asking a cat to run at the speed of a horse. It is just like that. So what we need to do, should we use the classical hardware like a transistor based hardware or a conventional way to run the quantum algorithms, or we need to have a quantum hardware, inherent quantum hardware? Why? The reason is that there is a basic difference between conventional computing and or classical computing and the quantum computing. That difference is conventional computing is a sequential computing which is unable to handle the huge data. In coming future, we'll be dealing with the data analytics. So it would be very difficult for this classical hardware to deal with. As I said, the transistor size is moving towards the size of the atom, right? Second thing, classical computing process the information in a sequential way, means one after another. As far as quantum hardware is concerned, it processes the information, or we can say that it carries out parallel information processing. So it will make the things faster. So it's why, this answer to this why is, it's always feasible. It's always logical, I must say. It's always logical. It's always logical to run the quantum algorithms on the quantum hardware. The IBM has taken a step forward in this. They have already produced some hardware in quantum hardware, and they are doing so, right? But enough is not done in comparison to the design of quantum algorithms, optimization of quantum algorithms. But people are running the quantum algorithms on transistor-based hardware or classical hardware. We need to move from this classical hardware to the quantum hardware. The reason is that parallel information processing and the quantum hardware is the suitable because it is inherent hardware which is suitable for the processing of the quantum algorithms or the quantum circuits. This is what the reason is. Now, as I said that, how to physically realize the quantum computing? Before we move on with the physical realization of the quantum computing, we need to take care of de Vincenzo's criteria. Unless any quantum hardware, let it be any kind of, it is a cavity quantum electrodynamics or superconducting circuits or Spintronics or any other which are supporting the inherent quantum mechanics based operations, they all have to follow de Vincenzo's criteria. What is this de Vincenzo's criteria? I'm just highlighting it. Actually, only 25 minutes are left with me. I will try to finish it. The first is storage of quantum information. The system should be scalable, or the hardware should be scalable in such a way that the information is encoded in a scalable system till the computation is performed. This is the storage of quantum information or qubit. The second criteria is initial state preparation. The hardware should have the ability, or the state of all qubits should be set to 0 before computation begins. So this is called initial state preparation. The third one is the very important, which is called isolation. What is this isolation? The isolation of the system from external environment. There should not be external effects like temperature effect or any magnetic effect or any external effect is needed to reduce the decoherence effect. So it should be isolated from the external effect. Spintronics plays an important role in this direction. Decoherence is defined as loss of information from a quantum system into the environment due to the environment effect. So this has to be isolated. So the hardware which is supporting the quantum computing has to have the isolation. The most important criteria is a quantum gate implementation. Right? The hardware should have the ability to realize the quantum gate. So what we can say that the individual qubit state isolation, manipulation, and control interactions are required. Right? Most important thing is when you try to realize a quantum gate on a quantum hardware, let it be any hardware, it should carry out that operation before the decoherence time is reached. It has to be done before. Don't it get exposed to the environment. Right? So that ability that hardware should have. And last but not the least, I must say it is the most important criteria, that is a readout. What is this readout? The scalable physical system or hardware should have measured the final state of qubits at the end of the computation, not in between computations. I would like to emphasize on one thing. It is always advisable to trace the quantum state at the end of the entire operation. Let it be how complex the operation is. You are not allowed. Why? Because the reason is that if you trace it in between, there will be quantum collapse. So it is always advisable to trace it at the end. Right? Now, as I said, I have spoken about the de Vincenzo's criteria. that information coding, state initialization, isolation, implementation, and measurement. There are different ways of realization of quantum computing: dipole trap, stationary and flying qubits, optical fiber coupled cavities, superconducting qubits, cavity based quantum network, and most important is quantum dot. I will emphasize on this. There are different ways. If you look at all these kind of realizations, they have the inherent quantum properties, unlike the transistor way or unlike the classical way. They have inherent quantum properties. If you look at this quantum dot carefully, one may ask a question: what is this quantum dot? It looks nice. The quantum dot is nothing but an electron is trapped in a cavity, voltage cavity, right? Or voltage well, you can say, right? Once the electron is trapped, its properties can be manipulated externally, or spin properties also can be manipulated externally to control its qubit state to achieve the quantum computing. I would like to say one thing at this instant: though the quantum computing looks attractive, equally its realization is very difficult. The one of the realizations is the spintronics. Now one may ask a question: what is the spintronics? Spintronics is nothing but spin of electron, right? Every electron has two spins. When you talk about an atom has a nucleus, right? So, and all of us know that electron revolves around the atom, right? Now this electron revolves around the atom, at the same time it revolves around its own axis, whether it is rotating in a clockwise direction or anti-clockwise direction, which is also called as a spinning electron, right? Spin. So it has up spin or down spin because of the spin magnetic moment. At the same time, the electron is attached with the nucleus, or which is called as nuclear spin. So there are two moments. One is a orbital magnetic moment at the nucleus, mu L, and second one is a mu S, spin magnetic moment attached with the electron, right? So we can say that there are two possibilities. One is the up spin and down spin, right? So every electron, if you look into this slide carefully, I have shown it. So when we talk about the energy, down spin and up spin electrons, there are two possibilities: up spin or down spin electron. When we talk about the electron, the quantum mechanical spin of an electron, right? The electron has quantum mechanical spin. Just now I have given you the example while discussing the qubits. The example of the electron spin, it's a pseudo vector. It has the polarization. Why? Because the magnetic moment that has magnitude as well as direction. Therefore, it is called polarization. Now, the behavior of electron spin and charge, spin magnetic moment in solid state devices are studied under the Spintronics umbrella. What are the different significances of the Spintronic umbrella other than the quantum computing? Now, the Spintronics is used in non-volatile data storage. Spin means magnetic, right? As I said, that magnetic moment, non-volatile data storage, high integration density. Why? Because memory and logic can be used on a same chip. You don't require to have a separate chip for the processing and the memory. You can have on the same. That's why integration can be in a high integration density. Information processing at high speed and low power consumption, as we talk in terms of magnetic moments only, right? So this is what the Spintronics in short. Now I will talk about physical realization of qubits with the help of Spintronics or spin qubit architecture. When we talk about the architecture, as far as the spin qubit architecture, I will speak in brief because I do not have the time. The spin qubits are embedded in the semiconductor channel. If you look into this figure carefully, there are different spin qubits, n number of spin qubits. They are embedded in a semiconductor channel. The semiconductor channel may be of copper or maybe of graphene, right? And on either side of these spin qubits, these spin qubits are nuclear. There are two types of qubits, electron spin and nuclear spin. As far as this particular architecture is concerned, the nuclear spins are utilized. So on the either side of these nuclear spins, the barriers are there. If you look at the De Vincenzo's criteria, what it says, the architecture should have the ability to isolate, initialize, implement, and read. So if you look at this architecture provided by or proposed by Brian Sutton and Supriya Dutta of Purdue University, they have provided everything which is required by the DiVincenzo's criteria, right? So this is one of the architectures, and I will not go into the mathematics again. You will not understand because it is not one day's work. It takes a lot of time to understand. So just I will briefly go through it. This is a single qubit rotation. If you look at the single qubit rotation, a qubit is on the either side of the qubit. There are two barriers, and there is a spin. What we can say, we can inject the spins from the left hand side, so that if the p barrier is lowered, those spins or those electrons will interact with the nuclear spin. Based on the spin of the electrons, the qubit state of the nuclear spin will be manipulated, will be operated. That is what I could say. I will not go into the mathematics. And that interaction is that alpha. How much interaction between the entered electrons and the nuclear spin, right? So this is what single qubit rotation. How when we talk about the rotation, we need to talk about from 0 to 2 pi. So if you look at that this oscillation, not oscillation, the rotation around of a z state, of a state which was earlier along the z, can be rotated around x-axis and y-axis. That is shown here. Again, that is qubit initialization is the first figure. Second is the qubit rotation or qubit manipulation. The second is two qubit entanglement. Entanglement is a process wherein we bring the both qubits in the same state, right? And if you trace it, it will go either way, right? Entangled state is not a 0 or 1. It is in between 0 and 1, right? So these are some of the methods. So similar thing we do, we lower the barrier which is on the either side of the qubit, and we allow the electrons to interact with both qubits. They will reflect it back. There will be a standing wave, and with the help of the standing wave, the qubits S0 and S3, which are shown here, will be in the same state. Right? This is what the entanglement waveform. There are some points where the both qubits are in same state, right? Now, the first task we carried out at the IIT Roorkee was how to model this qubit structure, or which was given by the earlier authors or earlier researchers in the literature. They have not provided the, what we can say, the general simulation platform. So we carried out the task of transmission coefficient matrix modeling of spin torque based and qubit architecture. So this was the architecture we proposed. The difference between previous architecture and this architecture was we have provided an input assembly with the help of spin Hall effect, right? And we said that if we use the spin Hall effect rather than the other conventional methods, it could provide the electrons which can be effectively interact with the spin qubits by lowering the barriers on the either side, right? So this is what the single qubit architecture. Now, as I said that the qubit has high barrier on one side and low barrier on the other side. We have proposed the heavy metal, the nanomagnet, and tunnel barrier. The role of the tunnel, you will, if you are a computer engineer, it's quite difficult to understand all these terms. The tunnel barrier is used to avoid the mismatching between two materials, right? So it helps to match the. Now, on the one side, there is a nanomagnet, on the other side, there is a channel, so that we can inject the electrons, spin polarized electrons effectively from the nanomagnet into the channel. The electrons will travel through the channel to interact with the qubit, and qubit state will be decided. As I said that there are two times, one is a relaxation time, another one is a coherence time. Both are shown in on the block sphere, right? So that coherence time is 0.52 milliseconds for the phosphorus donor. I will not go into these details. There is a isotopically enriched. So this was our first task, to model this single qubit through these matrices, singlet and triplet. These are the electron states, electron energy states. So these electron energy states are modeled as singlet state and triplet state, right? And with the help of that, we have obtained a generalized matrix T. And this is what we have achieved, a single qubit rotation for the pi by 2. So by varying the barrier and exchange interaction, we will able to reduce the number of electrons required for the interaction. So this is what the single qubit rotation. This is the interaction factor. Interaction factor means what? The injected electrons and the qubit which we have utilized, how they will interact effectively based on the electron velocity exchange interaction, that is J. So if we go on increasing this ratio, this exchange interaction and barrier height, this is in numerator the barrier height, in the denominator exchange interaction. If we go on increasing the barrier, there will be better standing wave in between barrier and the qubit, or between two barriers, to have an effective interaction. So this is what we analyzed. This is what the number of electrons required for the realization of single qubit rotation based on this ratio. Now this is a two qubit architecture. Why we use the two qubit operations? Mostly to carry out the entanglement operation. So what we will be doing here, from one side of a qubit, we will inject the electrons, and the barriers G1 and G2 will be reduced, so that qubits Q1 and Q2 will be interact with each other and will reach in the entangled state when number of electrons are injected from one of the sides, right? So this way we can obtain the entanglement. So one may ask question, what is the difference between previous case and this case? Earlier it was not modeled how to reduce the number of electrons required. That we have analyzed, right? So just look at the number of electrons are reduced if you go on increasing this ratio. But what we observed, due to this, there is an increase in error. So we carried out the error analysis. The error is increasing. That is, which is called C dash and C double dash. They are from the matrix, non-unitary components of overall spin density matrix. This was the first task. The second task we have already discussed, the reversible Boolean computing. Right now, how to use the quantum computing or spin qubit architecture to realize the reversible quantum gates. So let us talk about that. So before we move on to the reversible Boolean gates, we need to talk about single qubit operations on this spin qubit architecture, which we have explained just now. We realized Hadamard Gate, but this is a conventional way. Now we went through one of the literatures. We observed that these operations can be reduced. The reason is that the decoherence time, that is because of the limitation of the decoherence time, we need to reduce the number of operations to carry out as many operations, as many quantum operations as possible. This is a conventional way. What we did, we reduced it from 3 operations to 1 operation, that is Rx, Rz, and Rx. We used only Ry operation with the mathematics. Right now, this is a conventional C0 gate. As I said that there is a decomposition of the C0 gate. The conventional way of C0 gate decomposition is it requires 11 operations. You can see into this figure. It requires 11 operations. What we do, we designed a new C0 gate which requires only 7 operations. So at the C0 level, we reduce the number of operations from the 11 operations to the 7 operations. So there is a considerable reduction in computational complexity. That is a 36% number of operations are reduced at the C0 level. You can imagine if we use this C0 gate to carry out the complex task, complex computing, how effectively it will reduce the number of operations. So this is what we achieved. Then we achieved the 2 qubit operations like swap gate. Then 3 qubit gates such as Toffoli gate in a conventional way, in reduced way. See, just try to compare this Toffoli gate. This is a decomposition of a conventional Toffoli gate, and this is what we have done. How many number of operations are reduced? So this was a significant contribution to the scientific society. So then the Fredkin gate is a controlled swap gate. In the beginning, I did not tell you what is a Fredkin gate. It is a controlled swap gate. What is a controlled swap gate? It is a 3 qubit gate. If first two qubit states are 1, then the third will be, first is 1, then second and third will be swapped. This also reduced. So this table explains a lot. In case of C0 gate, we reduce the number of operations from 11 to 7. So there is a considerable reduction of 36.36%. Similar thing we obtained for the swap gate. We reduce the number of operations from the 32 to 21. for Toffoli 79 to 51, and Fredkin 101 to 65. Right? The reason is that the reason for carrying out this task is the decoherence time. Because of the limitation of the decoherence time, we have to carry out as many number of operations as possible, right? Or as many more number of operations as possible. And because of that, the execution time is also reduced for all of them. That is 10.58% for CNOT gate, 13.77% for swap gate, 14.30% for Toffoli gate, and 12.92% for Fredkin gate. Similar kind of a thing is for number of electrons required. It's natural, it's a bit of common sense based. If the number of operations are reduced, certainly the number of electrons required to carry out a certain gate, to realize a certain gate will be reduced. And we have calculated it as 9.25%, 14.73%, and 22.64% in comparison to the conventional gates. Now there is a concept of fidelity. Fidelity means when we talk about the output state, we need to talk about that output state in terms of the desired state. We need to know how close the output state is to the desired state. Suppose I want to have my desired state is for 1 and I am reaching 0.99. So that is what that we will represent in terms of fidelity. So what we have observed, due to the reduction in number of operations, fidelity is also improved. For the CNOT gate, the fidelity is improved. For swap gate, it is from 99.51 to 99.61 and so on. So fidelity is also improved. Now, let us talk about Boolean gates. I have already explained this Boolean computing. I will not go into it. Just I will show you how many number of operations we achieved. And we carried out the optimization also. How we carried out the optimization? When we individually realize the quantum gates, that is okay. But when these quantum gates become part of a complex quantum circuits, we need to talk about the interface between these quantum circuits. There are some operations after the decomposition of the quantum circuit. There are always some operations at the interface which are redundant, which can be removed, which can be merged. So you observe that there are some operations like single cube rotation around y-axis of one quantum gate and other quantum gate, that they can be cancelled at the interface. So two operations can be reduced. Similar kind of a thing if two single qubit rotations are there and they are around the same axis, you don't require to carry out the task in two ways, two different ways. You can do it in a common way by merging them, and similar kind of a things are carried out. So we carried out the reduction as well as optimization for the quantum computing blocks. They all are reversible Boolean gates. I have superscript R, that is AND R, OR R, XNOR R, NAND R, NOR R, XNOR R, half adder R, and full adder R. Just imagine for an AND gate, the number of operations are reduced from 79 to 49 after the optimal decomposition. So how many number of operations are reduced? 59, 6 times 30 number of operations are reduced. Can you imagine how efficiently we can carry out the task now? And just look at the full adder. The number of operations are reduced from 182 to 107. Almost how many operations are reduced? So this is what the second significant contribution to the scientific society. And we realize it in the Spintronic architecture. This is XOR gate, this is AND gate, this is OR gate, this is half adder, this is full adder. Now this is a Boolean logic. After that, what did we do? After realizing all these quantum gates and all these basic elementary blocks of reversible quantum computing, we put them on the complex quantum circuit. That is optimal decomposition of 2 qubit, optimal decomposition of 2 qubit OR gate and XOR gate to carry out different Boolean tasks in a parallel fashion. Parallel processing. What we say, what the quantum computing is? Quantum computing processes information in parallel, right? If you look at it carefully, we have given the inputs as 0, AB, 0, 0. At the output, we have obtained XOR operation. A we have achieved, B we have achieved, A into B also achieved, and one state is also achieved. So multiple operations are carried out in this optimal quantum computing. Now, the performance for the Boolean computing. You can see that this is a performance, the number of We have seen the transistors T1 and T2 for the injection purpose. These activities are also reduced. So we envision that a decrease in power dissipation due to reduction number of switching activities. So gate fidelity also improved. But what we observed as we go on increasing the complexity of the quantum gates, let it be utilization of quantum gates for the half adder and full adder, there is a bit reduction in the fidelity, 98.79 and 97.65 for the full adder. This is a bit of concern. But if you again reduce the number of operations, this fidelity can be improved. Now, I will not go through this reversible D-latch. It is similar like the previous one. This is a quantum circuit decomposition for the reversible D-latch. This is the realization of the reversible Ds for reset and set state. Now, these are the different cycles through which reversible D-latch has gone. What we have observed as we go on increasing the number of cycles, why? Because it is kind of a feedback kind of a thing. We give the output state as an input state. There is a slight reduction in fidelity as number of cycles is increasing, which results in small but incremental error. So what did we do? We put an error correction approximation. At that time, we did not have the error correction circuit, so we approximated. And what we observed, if we approximate, the fidelity can be improved from 99% to say some 97%. The most important, why I was running through the slides, I wanted to cover this spin torque based quantum Fourier transform. As I said, the quantum Fourier transform is the modified version of the Hadamard Gate. Now we said that Shor's algorithm is used for integer number factoring, and the quantum Fourier transform is an integral component of the Shor algorithm. Apart from that, there are several applications of this quantum Fourier transform, that is phase estimation, discrete algorithms, quantum key distribution protocol, multi-party quantum telecommunication, and quantum algorithm arithmetic. Therefore, quantum Fourier transform is a very, very important, and for that, its physical realization has to be addressed. What did we observe while doing this work? We observed that this quantum Fourier transform is not realized on the Spintronics platform. So we went ahead and realized it with the help of this quantum. This is what the quantum circuit was, the quantum Fourier generalized circuit. We have done it only for the 3 qubits. So we did these mathematical calculations. We obtained the decomposition with the help of this Nelson's book. This quantum computation and quantum information, you can treat it as a Bible of the quantum computing. Anybody wants to begin in quantum computing should begin with this Nelson book. So with the help of the decomposition, we obtained the decomposition of the quantum Fourier transform. Again, we use the reduction and optimization techniques. This is what the evolution of the qubit states, see, from 1 to 0 and 0 to 1. So these are some of the analysis. This fidelity also we have observed for a 3 qubit quantum Fourier transform, we can achieve the fidelity approximately 99%. Then also we have achieved the quantum Fourier transform periodicity estimation. What is periodicity estimation? If you look at this, for that purpose, you need to have the input state preparation. We obtain the input state preparation with the help of 2 Hadamard gates. We prepared the input state. We observed that if the input density matrix of periodicity 4, we can obtain the output density matrix of periodicity 2. So hence proved that whatever we have done for the quantum Fourier transform is absolutely right. The reference for that also given at the bottom of this slide. Now we have done further. Now my key insights. Now I would like to conclude. My key insights are quantum computing is the future of the computing. Computers will not require initial time to get started. Nowadays, you need the reboot time. But with the help of the quantum computing, you won't require. As far as technological advantages concerned, it has a huge impact in defense, intelligence, and supremacy in the field, which will change the strategic balance of power. Other than the weather predictions, quantum computing can lead to scientific breakthroughs or on commercial applications such as data encryption and even new drug discovery. As I said, weather prediction, financial analysis, logistical planning, and also in space discovery. They may make facets of artificial intelligence, such as machine learning, much powerful. Therefore, we can say that ultimately, quantum computing will have, or is, or do have, huge impact on the nation and our society as a whole. Thank you. Thanks a lot. Shikha ma'am?
Yes, sir. Yes, sir. Any queries from the participants, please? You may write your queries in the chat box, or you can raise your hand.
There are few queries in the chat box. Let me see what they have asked.
Actually, they are appreciating. These
No
are
question.
the appreciations.
No
questions.
question is there.
These are the appreciations for your talk.
I wanted the question so that I can move forward.
Yeah, actually.
Yeah.
But from my side, like
it
was really a
can
very
you share my
enriching
email
session.
with the participants so that they can directly write the queries to me if they don't want to do it now? Yeah.
Sure, sir. We will share your email ID with the participants.
It was
so that they can
time, but I hurriedly done it. I think so.
Yeah, but you have, taken us to the complete journey of the first generation computers to the, all the computing, Spintronics, and given the multiple dimensions for research and to continue the work in the field of quantum computing. It was really very enriching session for all of us.
Thank you,
I'm sure the participants will have definitely got some information so that they can work in this direction. And most importantly, like when they're doing the research, it is very important to know how we can compare the work, show the results, in the research articles and how to go about it. So you have really given a deep insight into it. Thank you so much, sir, for being here, for associating with us. And
I should thank
time.
you as well as my supervisor, Professor Brajesh Kumar Kaushik, sir.
Yes, sir.
Because of his supervision, this happened. Yeah.
Yeah. Thank you, sir. Thank you so much for being here.
Shall I leave, ma'am?
Yeah, please, sir. Thank you so much.
Bye. Where to leave?
It is top right, bottom right corner.
Yeah.
So our next speaker has already joined. We'll just wait for 5 minutes and have a break so you can have water and all. And we'll start the next session in the next 5 minutes, please. Dr. Ruksan, can you hear me?
Yeah, Professor Shikha, yeah, I can hear you well.
Yeah, can we try out if you wish to share the presentation, we can test it.
Definitely.
Yes, sir. It is visible.
Okay, I'll just put it in the maybe the full screen mode.
Yeah, sure. Dr. Ruksan will start the session in 5 minutes, please.
Yeah, sure. Fine.
Thank you so much. Dr. Ruksan, we are about to start. Okay, let me introduce. Hello, everyone. Welcome back to the second session of day 6 of Summer School on Quantum Computing and Applications. The speaker for this session is Dr. Ruksan Ul-Haq. He is a quantum physicist with more than 10 years of research experience in the areas of quantum many-body physics, quantum computing, high-performance scientific computing. He has published many papers and made seminal contributions to the research in these fields. Dr. Ruksan Ul-Haq gets invited at various conferences and workshops at both national and international level. He has diverse and vast experience both in academia as a researcher and industry as scientist. He was a lead data scientist for the forecasting project with Johnson & Johnson. He was selected as the co-founder of a startup company for quantum computing by one of the leading talent investors of Europe. Currently, he is working as quantum AI scientist with IBM, which has a legacy of the global leader in quantum computing. He is also the associate ambassador for IBM Quantum. We welcome you, sir, and request you to start the session. Over to you.
Very much, Professor Shikha, for kind introduction.
Sir, kindly increase your volume, please.
Okay, sure. So, Professor Shikha, is my audio clear, or do you see any?
Yeah, there is a glitch.
Okay, so how about now?
Yeah, perfectly fine now.
Okay, great. Okay, so fine then. Yeah, I will. Let me get started. And first of all, I'm very thankful for inviting me to have this session at this event, which is very interesting. I was going through the list of the kind of sessions. Very interesting, diverse kind of talks have happened. So good. So what we will do in this particular session, we will mostly focus on more on the industrial applications. I mean, we will try to see, okay, there is a lot of talk on quantum computing, and we will try to ask this question, and along the talk, we will try to answer it, whether there are some realistic applications of quantum computing in industry, in various domains, like as say finance, banking, or maybe manufacturing, or other kinds of domains. So first of all, we will take a look through some of the industrial applications, then we will take a deeper dive into quantum computing itself. So all of us know that there are in various domains, we have various kinds of problems which we face in terms of some of the challenging problems. Let's look at maybe the four of the important domains. One of them is which comes more from the point of view of the agriculture. In agriculture, we use these fertilizers, but as you may know, the process of manufacturing these fertilizers is very costly. It's an expensive and a laborious process. And what one would like to do from a this industry point of view, one would like to maybe make this process faster, make it more cost effective, and make it more efficient. So and also from the point of view of the speed, maybe make it faster as well. So that's one of the problem in one of the domains coming from agriculture. Similarly, catalysis is another domain in which we always are in the search of the better catalysts, and catalysts are used in various applications. And actually, there's a huge sector in which we use catalysis. Similarly, when it comes to the financial markets, banks, stock markets, and other kinds of such sectors. So it's also one of those kind of a challenging areas, because understanding stock markets itself has remained more or less a challenge, and one would like to understand and get a better control on these markets in terms of the predictability. So, or in terms of understanding how economies will grow. So this is a big one of the central problems of modern societies, to understand our financial markets and understand our economies better. And we just pose it as one of the problems where we can invoke various technologies, including AI, or maybe later on we will also see what quantum computing can contribute in solving these problems. Similarly, another, when it comes to the medicine and the drug discovery, we know it's once again a very critical sector for all of us in terms of healthcare, and designing the drugs, the corresponding and effective drugs for a particular disease. And we are painfully aware of this particular problem through COVID. Through last couple of years have shown us the importance of drug discovery. Any disease can come up with, and we need to have an effective system in place so that we can quickly come up with the corresponding drugs for that disease. So drug discovery is also once again a very central very important and critical aspects of modern societies, especially the healthcare. So these are like 4 sectors I have focused upon, because all of them are very critical to our society. But there are many more important challenging problems which are once again very important. Now, the question which we are trying to ask is, and in today's talk, we're asking the question, can quantum computing, or does quantum computing has the potential of, at least we would not say absolutely solve all of these problems, that will be too overambitious statement to make, but at least to leverage this technology to come up with a better solutions so that we can make more progress in these sectors. And we are going to focus on that. This is the background which we are setting for rest of the talk. Okay, so which means we're identifying 3 important areas from these industry sectors. There are 3 important areas of application of quantum computing, and we want to see whether quantum computing can have applications in these areas. So one of I said about catalysts and the drug discovery, they will come in the domain of the physical or a computing problem is how can we simulate these quantum systems, because whether you have the catalysts or you have the molecules, they're all quantum systems. They are quantum chemistry systems. And to solve them, it is essentially asking, can we simulate these quantum systems? Can we simulate these molecules in a more efficient and a better way on quantum computer rather than on a classical computer? Do quantum computers have a better efficiency? Do they have some sort of an advantage, which we can call as quantum advantage, in simulating these molecules? And I will motivate you that the answer to that question is yes, that quantum computers come up with much more efficiency, some sort of we will see it's an exponential advantage in simulating these quantum systems. And if you try to simulate these quantum systems, molecules, catalysts, drugs, medicines on classical computers, it is a well-known challenge on classical computers. And when I'm talking about classical computers, I mean the fastest supercomputers which we have access to. And then other problem is more of asking this question, okay, artificial intelligence, it looks like a very mature technology by now, but the problem with the artificial intelligence or deep learning models is always that they are computationally very, very expensive. Some of these models have millions of parameters to tune, and it is in terms of the computational resources which you need to consume to do these calculations and computations is sometimes immense. And only the kind of corporations or big organizations have sometimes access to these computing resources, and it is not something which everybody can do. Everybody does not have access to something, let's say GPUs or tensor processing units. So therefore, even though artificial intelligence it does amazing stuff, these deep learning neural network based models, but there is always this challenge of the computational cost associated with the deep learning. So the question here is that, is it possible that we can combine artificial intelligence with quantum computing and try to bring some sort of a hybrid architecture which will make artificial intelligence or deep learning models maybe less expensive, or if possible, make them better, more efficient, faster, and that kind of stuff can be done. So this is another problem. And once again, maybe if we have time, this area is called nowadays quantum machine learning, or sometimes also called quantum AI. And it has been demonstrated by early research which has been happening, that there is at least some promise that if you use quantum computing, you can combine, and if you can combine classical neural networks with quantum computing, there is surely some promise that we can get better results. But however, I think I should say it is still a research. It's still something which is going on in research. We still maybe have to wait a little bit to demonstrate that power in ML and machine learning and AI. Now, another problem which is, once again, it's very central problem. It's something which always comes up whenever we try to solve any business or industry problem, is something called optimization. And I think each one of us would have come across optimization problem in our lives or whenever we solve these business problems. So optimization is once again, like is when you try to optimize the transportation, you try to optimize the supply chains, or you do any kind of optimization, be it small routine daily work, or maybe in a highly scalable some business issue. So we always need optimization. And classically, there has been kind of, I would say, sophisticated methodologies, algorithms in place which tries to solve these optimizations. But once again, optimization is a very complicated problem, and there are always many parameters which one has to deal with and solve the optimization problem. Once again, the natural question arises is that, okay, with these quantum computing offering us these advantages, can we use these quantum computing power to solve the optimization problems better? And this whole area is nowadays called quantum optimization. And at least once again, there has been some, I would say, some of the aggressive work which is happening in quantum computing application is optimization is one of those areas. And so quantum optimization is a very active area. And some of the earlier results suggest once again that quantum computing may have it can offer us some of the advantages in solving optimization problems. So these are like three main important areas, but these are just areas. If you look at in terms of the actual use cases in these various areas, there are multiple of them. There are hosts of use cases associated in each of these areas, and I have just listed some of them, and definitely there is many more use cases that people are exploring. Various companies are exploring these use cases depending on their domain. So when it comes to simulating quantum systems, you can see what the use cases are in terms of the, as I said, drug discovery is one of them, understanding the biomolecules like as protein structure, similarly disease risk prediction is, or one of the important things is when it comes to nowadays, we are talking about the electric vehicles. So electric vehicles rely heavily on the batteries. So one would like to get better battery designs, better battery materials, so that they give us more efficiency and help us in getting to the electrical transportation. Similarly, manufacturing defect identification, that's one of the pain points which any company doing manufacturing has. You have to have a better control on whenever you manufacture some product. You would like to understand better whenever that defect happens, so you capture it beforehand. So similarly, if you come to artificial intelligence, there are many important use cases where quantum computing can play a role, and all of these things are being explored actively as of now by the researchers and companies. And like as the portfolio management is one of them. Similarly, the fraud detection is one of the things which is a huge challenge for the banks. Catching the fraud detection is, and though AI-based solutions are available, but as I said, there is always need for making them more secure, making them more transactions security for the transactions, and similarly getting the fraud detection is making a better mechanism for catching the fraud, doing the fraud detection. And similarly, in the optimization domain, there are many use cases which we can work towards. Okay, so and then finance is one of the domains where both from artificial intelligence and quantum computing, there's a lot of interest. This area is, they call it quantum finance. Now, I want to take you a little bit back into the history. In 1980s, that's when maybe the first discussion is around quantum computing started. And this well-known physicist, Richard Feynman, he was just thinking about that there's a need that if we want to simulate, if we want to understand, better understand these quantum systems, and quantum system can be a semiconductor, it can be any material which has some interesting properties. All of them are, as we know by now, the physics side of them, we know these quantum materials, whether they are electrical batteries, they are semiconductors, superconductors, or even the quantum computing hardware itself. All of this stuff is quantum, and we would like to understand them better. But if you want to try to do that, that's what these scientists were thinking in 1980s, that there is a need for developing what they used to call as quantum mechanical machine. Okay, so this need was felt right in 1980s, especially they were dealing with this problem of not being able to simulate quantum systems on classical computers. And since then, people have tried different ways of sophisticated algorithms for doing simulations on classical computers, but the problem and the bottleneck still remains there. And this was why I am mentioning this particular example, is because this acted as some sort of a kind of a motivation for researchers to think more seriously about developing quantum computing. And so simulation of quantum materials has remained one of the most important and promising areas of application of quantum computing. And it offers theoretically, if you look at the algorithms we use for quantum simulation, it offers what we call as exponential advantage. So which means that if you do quantum simulation on a classical computer and then you do it on quantum computer, so on quantum computer, it's going to be, if not exponentially faster, but the reduction in the cost is going to be exponential. So you will need exponentially less resources on quantum computer in terms of the memory, in terms of the computing power. So therefore, there's a lot of interest in doing simulating these systems on quantum computers. So these was just some of the more things from the same paper. Okay, now since we have talked, I have taken you through some of the applications where quantum computing has a promise. So we want to take a break and ask ourselves a question. Okay, because I have been mentioning classical also and quantum also. So let us ask this question: why do we need quantum computing at all? So in this, I just want to, in this kind of a Venn diagram, I just want to say that it is not that we need quantum computing for every problem which we are facing. To say that will be also kind of exaggeration and factually incorrect. There are problems which classical computers can solve, and they can solve them very well. For those kind of problems, we do not use quantum computers at all. But then there are some problems which classical computers cannot solve at all, like as the problems like as where we use Shor's algorithm, cryptography like problems. So they are and similarly simulating quantum systems, simulating various kinds of systems. They can include drugs, they can include proteins, molecules, and other kind of systems. And especially the materials which are needed for modern industry. Let's say you have a laptop in front of you. Many of the materials which you use for laptop, including the magnetic RAM it has, including the battery which it is using. So all of those materials are quantum systems in nature, and understanding them better and simulating them better, classical computers do not do a great job in simulating them. And we will surely need quantum computers for such problems. However, there is going to be a domain in which we need to rely on a hybrid model, in which we have to use, we can't just use quantum computers alone, we can't just use classical computers alone. Maybe it will be better to bring both the worlds together and have some kind of a hybrid model, and that will be the best solution for those kind of problems. So therefore, this Venn diagram is quite indicative to understand what is the actual space where quantum computing is going to have a lot of promise, lot of applications, and is going to go beyond classical computing. But simultaneously, we should be also aware of the fact that there will still be some of the problems where maybe the hybrid model will work better. And I also want to take this opportunity to mention that most of the algorithms which we are developing as of now in current era, which technically is called the NISQ era, NISQ, which stands for Noisy Intermediate Scale Quantum Computers. This was a term coined by John Preskill. So because the hardware, the current quantum hardware is still, it's still intermediate scale. We have the qubits around, maybe around 100 or something like that. So I would say on the current hardware, the best algorithms which we have, which we can run or develop, are called a NISQ algorithm or variation algorithms, and they have a hybrid character. They are not always like the algorithms which we use for quantum machine learning, quantum finance, quantum optimization. So they have this hybrid character. And that thing I think is very important to note, because they are not like as purely quantum algorithms. It's not everything is quantum over there. It's like we have the both hybrid classical and quantum computing models coming together, and then we build the hybrid model, and that really works good on the current hardware at least. But as we scale up, as we go along, I think we can explore algorithms like Shor's algorithm, maybe other algorithm which have the exponential quantum advantage. Okay, now I think I motivated you in terms of what quantum computing, in terms of the promise which quantum computing has, and giving you some specific and concrete examples from the industry where quantum computing can have an important role. I just want to mention, this is one of my favorite documents when it comes to, okay, you want to say, is there a place where I can go and learn more about these industrial applications about quantum computing? I would say you may think of me as a biased because it's a document created by IBM, but I think apart irrespective of that, if you take a look at this document, it's one of the finest documents which I am aware of when it comes to looking at what are the industrial applications. You can see the link over here. I would recommend all of you take a look and see for yourself the expert point of view on where are the applications of quantum computing in terms of when it comes to industrial applications. Okay, so this I just mentioned for that. And it basically this previous document, it also doubles this whole decade, which starts from 2020 all the way to 2030. This has been called the quantum decade, in which the quantum technology year after year will become more mature, and we will be there to witness the so-called quantum advantage, or maybe the exponential quantum advantage, which quantum computers will bring to the various problems. So, and it has a discussion around that. So check it out. I am sure you will like it. Now, we would also like to, in this quantum decade, what is the development roadmap by let's say IBM? Similarly, the other companies have their own roadmaps. So this is
excuse me.
Yes.
Can you make it a slideshow?
Yeah, so that's I mean, there is, there's a Zoom kind of that Zoom tab is there. Fine. I'm not able to go around it. And the button for slideshow is on the top of my PPT. So I'm not able to go around that.
Okay, you just click on the PPT slideshow.
And that's what I'm saying, Shika ma'am. It's behind that bar, that on the Zoom there's a taskbar. Yeah.
Okay, fine. It's fine.
Yeah, I tried to do it, but that would have been the best. Okay, yeah, I'm sorry for that inconvenience, but yeah, that's how it's working for me as of now. Okay, so, and in terms of the development roadmap, we are already, I just want to recall, in IBM quantum computers became public in 2016. That's when they had made it public. You can, what is nowadays called IBM Quantum Experience. You can create an account with IBM, and they use it to give you access for maybe, let's say, 4 or 5 qubits machines. But since then, you can see the year after year, there have been many developments, and we are in 2022. By now, you would have heard last year, there was an announcement or something called a Qiskit runtime, which is like, okay, if you want to run your quantum computing applications or some programmers on IBM machines, now using the Qiskit runtime, there is at least 100 times speed up. So if you, without Qiskit runtime, you run, and if it is a speed X, but if you run the same quantum program on Qiskit with Qiskit runtime, it becomes 100 times faster. And it has been demonstrated at one of the important quantum algorithms, which is called the VQE. For that one, it has been already demonstrated. And interestingly, there's a lot of documentation around Qiskit runtime as well. So that's happening on quantum software stack side. On the hardware, you see year after year, there is this development in terms of the number of the qubits, which is, in fact, it's not just number of the qubits, it's also the quality and the scale. So you will see in 127 qubit, I hope that announcement you would have already maybe come across. But as we go along, the next kind of a milestone will be going to 433 qubits as we go along, and it is coming very soon. So this is just to give you a sense of where we are going as we move through this decade, the kind of the quantum hardware, how is it going to scale, and similarly the quantum software, the quantum programs, in terms of where we are going. In IBM, there's a lot of focus on something called dynamic circuits and some circuit knitting, kind of these programmers. So that, and similarly, one another thing where there's a lot of focus is in the current hardware, you will see always these qubits are noisy, and we need to develop some schemas in dealing with those noisy schemas. And that's called error mitigation or error suppression. And that's also something which is very, very important in the current for the current hardware. And it's also kind of an important focus in IBM and other places as well. Okay, so this is public. You can see it, and let's keep on going. In interest of time, maybe would like to shift a little bit. We want to, this so far, it was more of a motivational of understanding, okay, quantum computing has these industrial applications, what is the promise of quantum computing, and how does especially I'm very fond of asking this question: how does classical computing, which has more or less it's a very mature technology by now in terms of AI, or we have methods and algorithms for optimization, or we have some other classical, the whole classical computational paradigm. The question is, how does it interface with the new paradigm, with the, it's a different kind of a computational paradigm, what is called quantum computing. How do these two different models of quantum computation come together, and how do we leverage them so that we take the advantage of bringing them together? So that I think I would emphasize upon, because it's not like what comes in many times in the general public, that okay, quantum computing is going to replace everything. I think that will be that's not the case, at least as far as I can see. So the best case is there may be some quantum applications where we have pure quantum computing applications, but there will be many situations where we bring both the models together. Okay, so far so good. Let's so Shika ma'am, are there any, can I take a pause? Are there any questions at this stage, or shall I move on?
So please move on. They'll be writing their queries in the chat box.
Okay, that's great. Okay, in the classical computing, we know where all of us are familiar with what is the notion of fundamental notion of a bit, which is like we have, that's a basic unit of information, and we just represented it in a binary representation. But now the time has come that what quantum computing tries to do is like go beyond this kind of a domain in which we have this, what now looks like from a quantum computing point of view, it looks like a bit restricted representation for quantum information. So we want to go beyond, and I want to give you a sense of how restricted it is. So how limited the capacity of classical information is. If we, let's say the coffee, which we take every day, we want to say, okay, I want to take this coffee molecule and want to simulate it on a classical computer. Just want to see its property. Let's say energy configuration is maybe some other properties and all that. So if we want to do that, okay, and we someday wanted to go to write program and simulate it on a classical computer. Let's say how much of kind of information it takes to simulate the caffeine molecule. So it will take on a classical computer, it will take you around 10 raised to 48 bits to represent the energy configuration of a single caffeine molecule. And 10 raised power 48, I don't know what we call it. There's no name for it. So it's such a big number. And it is, as they say, 1 to 10% of the total number of atoms in the Earth. That is the 10 raised power 48. So these many bits of information it will take to store the information about the energy configurations of single caffeine molecule. Okay. So now how about quantum computing? What happens in when you try to represent the same information in qubits? It will take you still a good number. It's not a small number, but it is just 160 logical qubits. And you compare it with 10 raised power 48. You can see the reduction in terms of storing information on qubits. That gives you a sense of how effective or how efficient it is to store information in qubits as compared to the classical bits. So that is why the classical bits, the classical bit representation is very limited. It is not a very efficient one, and there will be cases where we would like to shift it to qubits. Okay.
I have a query. Like, what is it that makes that we are able to store 10 to the power 48 bits into only that kind of information can be accommodated in 160 logical bits? Like,
oh, okay, yeah, good question. I am just one slide away from that answer. So let me just talk about this one, and then I will come to the answer. So I just want to also, because one of the good ways of understanding quantum computing is always asking this question: what is the correspondence between quantum computing and classical computing? And seeing, okay, the conceptual structures, at least the structure which we have on the classical computing, where we have bits, then we have the logical gates, we have the logical circuits. So how much of this structure still remains there? Because essentially both of them are computers. So so some of the structure should remain same. So as I said, the bit on classical side gets replaced by qubit. Similarly, the logic gates, which we have on the classical computing side, they will get replaced by the quantum gates, but there are in any computer, there are always logic gates. So same is the case with a quantum computer. And then we will have the circuits, like as we have in the classical circuits, we have these various gates, we have the bits, and then various gates being applied on it. Same thing goes with quantum computing. And here is a visual representation of what a qubit looks like. And I will try to answer the question which Professor Shikha asked, is what is it that, I mean, how does it happen that the qubit becomes such a large space for storing information that instead of using 10 raised power 48 qubits, you can just use 160 qubits and still store the exactly same information? What makes qubits more efficient? To answer that question, we have to remind, let's see what's happening in a qubit. So this whole sphere, which you see on the screen, is called the block sphere. The technical name for it is the block sphere. And if you look at the classically there are only 0 and 1 state. These are the only two logical states in which information can be stored, in which a logical computation or logic can be done. Okay, these are the only two possibilities which you have on the classical side, which means if you have to store information, you have to use 0 and 1 states, logical states, to store your information. That's the only way on that. So it's like a more or less a black and white world on the classical side. Now, when it comes to quantum computing, every point on this block sphere represents a state which is as valid as 0 state and 1 state, which means every state on this block sphere is a logical state which can be used to store information and which can be used to do computation. Fine. So the answer to the question, why is it that qubits are more, they have a more kind of a space, is because in a qubit is not just one state. Qubit is a one single quantum state used for this full block sphere. But in this state, there are many logical states, many states in which you can store information. And you can see there are infinitely many of them on the block sphere. That's why we say, whenever we talk about quantum systems, we say they have an infinite dimensional Hilbert space or state space. So it is this infinite dimensional, or maybe on a finite quantum computer, it means finitely large. It's still a very large number of states which are available to you on every qubit, in which you can store the information. I think that's the answer to that question. Having more logical space in which you can store the information and do the computing, that is the reason why quantum computing is you need less number of logical qubits as compared to the classical bits. So is that clear? Does it answer your question?
Yes, sir. Thank you.
Okay. So now similarly, like as we have on the classical side, we have the quantum, the circuits. Similarly, on the quantum computing side also, these two, you see there's something called Q0 and Q1. This is like qubit number 1 and qubit number 2. And that's how we represent them, at least in the Qiskit. And then you see there is H. There are these, the sign is a bar with a plus sign. And then there is this particular red box over here. So these are all quantum gates. H is something called, we are familiar with, it's called Hadamard Gate. And this bar with plus sign is the C0 gate. These are like quantum equivalents of the logic gates which we have on the classical side. Though we don't have any Hadamard gate on classical computing side, so you can think of it as essentially a quantum gate. But we have the controlled NOTs on the classical side. Similarly, we have NOT gates, controlled NOT, AND, OR. So all of them have quantum equivalents. So this is how a basic quantum circuit looks like. And this is what you run on a quantum computer. When you say, I am doing quantum computing, essentially it means developing these quantum circuits for your application and then running these quantum circuits on a quantum computer. And we will decouple them a little bit more. We'll try to understand these a little bit more. But one thing, one difference, we keep on hearing that quantum computing is different from classical. Let us see how. First of all, we saw that in quantum computing, we have a larger logical space available to us as compared to the restricted two-dimensional space on the classical computing. That is the difference number one. Second difference is that when you come to the quantum computing side, so you have this, your system can be in any state, any of these states in middle of 0 and 1 also, any state on the block sphere actually. And we represent it mathematically as alpha times 0 state plus A times 0 and B times 1. And 0 and 1 is nothing, but these are like, we call them states. These are vectors essentially, nothing but vectors, the usual vectors. So these are two vectors, and alpha and beta are arbitrary numbers, which means these states, a times 0 plus b times 1 is any point on the block sphere, and this is the quantum state which we have. But when you do a measurement, measurement is actually that operation which takes you from quantum information to the classical information. So earlier, before you do the measurement, information was in the quantum states, so it was the quantum information. But you have to do a measurement eventually, because when you do the measurement, you will always get either the 0 or you will get a 1. The answer will be always in the 0 and 1, okay, or some kind of a, which is like with some probability. The 0 state will be with some probability and 1 state will be with some probability, and the probability itself is a classical number. Okay, so this is difference, because essentially in quantum computing you have this probabilistic side to the computing, which is not there on the classical side. Classical algorithms, most of them, or deterministic algorithms, you don't deal with probabilities. You have the algorithm, you run it, you get the numbers. So that's it, and you don't need to do any kind of a measurement. So this is another difference. You always see this measurement operation as an important quantum gate on the quantum computing, and which makes it different because you have the associated probabilities coming in. So you can think of quantum computing as essentially a probabilistic model of computing. Okay, and that's very, very important. Then now I just want to show you over here what happens. Okay, we are this X gate you see over here. It has a particular meaning, but it's called the poly X gate in quantum computing. But logically, it is, from a logic wise, it is called it is the standard NOT gate, which we are familiar from the classical computing. In NOT gate, what classically does, it takes your maybe one state and takes it to the 0 state. Similarly, it takes 0 state to the 1 state. And same thing it does here also in quantum computing. Nothing more, nothing less. It does the same thing. It takes, as you can see, initially our state, our quantum system, our qubit was in the 0 state. It was pointing upwards, and we applied the X poly gate, the NOT gate, the quantum NOT gate. And then what happened is that it just shifted it from 0 to 1. Okay, which means early when we would have calculated the probability before we applied the quantum gate X, the probability would have been 100% for finding the quantum state in 0. But after we did the measurement, the probability for finding 0 is 0 actually, and probability for finding qubit in the 1 state has become 100%. It has become 1. Fine, that's what happens. And this is what happens in gates. And if you look at it visually, you will see the quantum gates are some kind of a rotations, because earlier this vector was upwards. Now, after we applied X, the vector got shifted towards down, vertically, exactly vertically down. So you can also, maybe it helps us to think about these quantum gates. They are some sort of a rotations which is happening on the block sphere. Okay, at least the single qubit gates can be thought of as rotations. Okay, so this was more about the gates and the basic kind of a quantum computing. And now we want to move on and do what we take a little bit deeper dive on some other important properties, because now we are trying to answer the question, what makes quantum computing more powerful? We saw there are qubits. We saw there are quantum gates. We also saw there is some sort of, it's a probabilistic model. There are probabilities coming in, which are important. And now another ingredient for making quantum computing very powerful is something called a superposition. And it is actually this superposition which was leading to all those states in between 0 and 1. In classically, you can't take like as a superposition between 0 and 1 and get a valid logical state. It is not allowed, because they are mutually exclusive. You have 0, you can either have 0 or you can have 1. But in quantum computing, you can have these states in between, which are lying in between 0 and 1. They are still logical, as I was saying, they are still valid logical states. And these states are called superposed states. These are like, they come out of something called a superposition. And superposition is nothing but mixing together, combining together these states. Because as I said, the states are mathematically represented in vectors. And you can always do a vector addition between two states and see the resulting state is also a valid quantum state and hence can be used for quantum computing. So superposition is very, very important. So essentially it means that you can combine the states in the quantum computing. You can combine these states together and then result in new states which are still the quantum states, which is still a valid quantum state. Okay, so but interesting thing happens as we go along, as we try to do this superposition maybe with more states, which we will try to do. But here I want to illustrate once again. Okay, when you earlier we did a measurement with 0 and 1 state. We had our qubit initialized in 1. We did a measurement. We found that it is in that particular state with 100% probability. Then we applied X gate and it got shifted to 1. We did a measurement again. We found it is in the another state 1. But if you have a superimposed state and you want to do a measurement again, what will be the outcome of the measurement? Okay, because now the state is in some sense it is in the 0 state, is in a mixed state. It's like some part of it is in 0 and some part of it is in 1. And you do measurement, you will see that you will get some probabilities, and those probabilities will be proportional to the coefficients in front of them. So which is like, in fact, more precisely, the probability will be the square of the modulus of A and the square of the modulus of B. So that is the precise relationship between the coefficients in the state and the probabilities. Okay, so I mean, because if you say, okay, I want to make both of them equally probable, then maybe you have to use the same coefficients, and in this case you can write it 1 by square root 2, 1 by square root 2, and it will make it equally probable. Okay, so that's how you do a measurement on a superimposed state. So let's keep going, because the interesting stuff will happen when you have 2 qubit states. Now you have 2 qubits and now you want to do superposition again, and something very interesting happened when you just reach this non-trivial number, which is 2, and you bring 2 qubits together. Now if you have 2 qubits, the way we represent them is like 0, 0. Remember, each qubit has 2 states, 0 and 1. And if you have now 2 qubits together, which will mean you will have 0, 0, you will have 0, 1, you will have 1, 0, which will, and 1, 1. 1, 1 will mean both the qubits are in the state 1. 0, 0 means both the qubits are in state 0. And 0, 1 means the first qubit is in state 1 and another qubit is in state 0. Similarly for 1, 0. Okay, if you have such kind of a situation, okay, what happens in that case? So something interesting happens in that particular situation is you may by using the superposition, you can take these 0, 0, 0, 1, 1, 1, and 1, 0. These are called basis states for 2 qubit system. You can do superpositions between these basis states. And when you do these superpositions, you will come up with states like this. 1 by root 2, 0, 1, and minus times 1 by root 2, 1, 0 state. And similarly, 0, 0 plus 1, 1 state. And when you look at these states, they are very special. What is special about them, I will explain. But I want to say that this is the example of what you would have heard a lot about, which is called entangled state. And entangled states are very, very important in quantum computing. So this is like an important computational resource. This is like as a memory, computational power is a resource for computing. Similarly, entanglement is another important resource when you do quantum computing. But what do I mean? I mean, we would have heard about the entangled states, but what does it mean more precisely, what is entanglement? So entanglement is this property that you have the 2 qubit system and you have got a superposed state. You have superposed them in such a manner that the resulting state which you have, it cannot be decomposed into 2 individual states. If you have a situation like this, that the joint state of the 2 qubit system is such that you cannot think of it as any kind of a product between the 2 individual states. If you have a situation like that, then your system is called entangled. More or less, it means that the whole system, the whole 2 qubit system behaves as one single quantum system, and you cannot think of it as made up of 2 single qubit systems. Okay, that is the situation what is called entanglement. And entanglement is very, very crucial. It is for many, in fact, all the quantum algorithms which we use, entanglement is the basic important primitive which gives them computational power. So therefore, entanglement is very, very important. And as we keep going, so And then later on, if I don't know whether time permits, but I will later on try to show you how do you implement this. If you want to implement, you want to say, okay, I'll go on a skit, I will go on IBM quantum computer and try to get one entangled state. Let's say one of these states which I was just showing, you want to implement it on quantum computer, I can show you that. Let's see how far we can go. And then the other component, this was like we were talking about states. We talked about you can superimpose them in quantum computing. Then if you use superposition principle, you can get something called entangled states, which are very, very special states when it comes to doing computing. Okay. Then the other big component in quantum computing is surely the what's called gates or operations. And on the quantum side, as you would expect, there are definitely new quantum gates, which you don't see on classical side. Very similar, like as in quantum computing, we have the new kinds of states, entangled states, which you do not get to see on the classical side. Okay. And what are these new gates? We'll see one of them. This is called the Hadamard Gate, and maybe we can explore some of its properties. Okay, so this is important to note that on the quantum side, we have the new gates, and this actually it is this Hadamard, which is used to create the superimposed states. Because what Hadamard does, if you take the state 0, it puts it in a superposition between 0 and 1. Okay, some kind of a superposition, and same thing when you apply it to the one state, it makes another superposition. So Hadamard, as you can expect, you will see, you take any textbook, any paper, you will see Hadamards. You will see Hadamards always there. The reason is that Hadamard is that particular gate which helps us to create superpositions on quantum computer. In terms of from a quantum programming, you can program superpositions on quantum computer by using the Hadamard gates. That's why you see them always there. And that's also one of the reasons why Hadamard is a quantum gate, because it gives us superpositions, and classically we don't create superpositions between logical states. So there are now, we talked about qubits, we talk about quantum gates, we also talk about superposition and entanglement as very important. Entanglement is very computational, very important computational primitive. Now we can keep on going and ask another question. Is there something more which makes quantum computing more powerful? And it brings us to another thing, which I'm not very sure. Have you thought about seriously about it? It's something which you learn maybe very early on in physics, which is like interference. Because you would have heard from your physics lecturers that whenever you have superposition, typically when you have superposition in waves and oscillations, they do interference. So when I say I have quantum states and I can superimpose them, does it mean I can create interference patterns with the quantum states as well? And the answer to that question is yes. And it maybe those of you who would have studied physics side of it, you heard of double slit experiment. So with the quantum states, you can create these interference patterns. The question over here is that, okay, what is the role, what is the implications of creating interference patterns in quantum computing? What does it do? And let's take a look. We have like 8 states over here. This is like 3 qubit system, and 3 qubit system has 2 raised to power 3, because every qubit has 2 states, 2 basis states. So if you have 3 of them, you will have 8 2 raised to power 3 states possible, and we write them as 0 0 all the way to 1 1 1. Okay, so now if you have this, all of them, as you can see on the vertical axis, you have the probability amplitude, which more or less tells you how that coefficient in front of the state. So they are equally probable. None of them is kind of more special. We have just deliberately colored one of them as red, and I'll illustrate why is that the case. Okay, so you will see what happens is that in many quantum algorithms, we try to, let's say if you have heard about something called a Grover's algorithm. In Grover's algorithm, what we try to do, we want to identify one particular state, okay, and we want to highlight that and amplify it. How we do it is, we basically, the first step in doing that is you invert the amplitude, fine, which means something needs to be changed, so that earlier this amplitude it was pointing in the maybe up direction, but now it's pointing in the reverse direction. What exactly happened? And it's not something in the amplitude which changed it, because amplitude is more or less once again same. So something has changed in the qubit which created it to move in the another direction. And what is that? That is called the phase of the qubit. And this phase of qubit is very important. I think I just heard a part of a earlier talk was talking about maybe quantum Fourier transform. In the quantum Fourier transform, we leverage these phases of the qubits. Okay, they're very important. So what has been done? Nothing has changed in the amplitude. Only thing that was done to this particular qubit 0 to this particular state 010 is the phase of this state was changed. And we do that in algorithms. There is something called, maybe if you are familiar with something called a phase kickback mechanism in quantum computing. So using the phase kickback, it is possible for us to change the phases of the qubits. But it's a controlled operation because we need to know for which qubit you want to, for which state you want to change the phase. And that's why it has to be a controlled operation. And we do it for this particular state, but phase is changing. And that's what I want to emphasize upon, that in quantum computing, you would have learned about phases in maybe physics, but you may not know that phases are very, very important in quantum computing. And this is what we are doing over here. We are just playing with the phases. Nothing happens to the amplitude. And as you remember, amplitude is directly proportional to the probability of finding the system in particular state. So nothing is happening in terms of probability. Nothing has changed at this stage. It is just that the phase has changed. And why are we doing these kind of changes? Because once we have identified, once we have changed the phase, later on what we can do, we can also change its amplitude. Okay, there are ways of basically bringing it back into the same direction, which is like we have done some sort of a rotation, brought it back, or some sort of a reflection and brought it back into the original direction. And then we have also done an amplitude amplification. And this amplitude amplification is one of the important quantum algorithms, which we use in Grover's algorithm, we use in many other places. And the way we arrive at amplitude amplification, one of those things rely on changing or tinkering or playing with the phase of that qubit. So the phase of the qubit is a quantum property. These phases are essentially quantum properties of these qubits, and you can play around them and create an interference pattern. What it means basically is that, as you see in interference pattern, some of those places become brighter and some of them become darker. So in that analogy, you can think as if this particular red state is now on the brightest spot, and all the other ones, you can see their amplitude has now decreased. Earlier it was up to the mark, up to this line. Now all the amplitudes have decreased, and this particular state its amplitude has been enhanced or amplified. And now this is the state which will help us to do, let's say, do Grover's algorithm or amplitude amplification. So this is where interference pattern is being used to arrive on do a particular quantum task, which is called the amplitude amplification. So what this example or what I'm trying to illustrate over here is the third ingredient in quantum computing or quantum algorithms is something called interference phenomena, quantum interference phenomena to make it more precise, which you are already maybe familiar with from your maybe physics lectures. Okay, so and then I'm going to now shift the gears a little bit more. So any questions, any urgent question you want to any doubts or concerns at this stage? Okay.
Any queries from the participants? No.
Okay, let's keep going. Now I think just to summarize so far what I covered, I just in this kind of a little bit of an introduction to quantum computing, I want to highlight certain things which you may not usually take a deeper look at them. Is like in quantum computing is essentially there are some aspects. First is the qubit itself. Then there is we have new kinds of gates, in example being the Hadamard being one of the representative of them. And then we have the special states called the entanglement states, which are used for doing quantum computation. And we can do those things which are not accessible on the classical side, because on the classical side you don't have entangled states. You can't do those you can't achieve those kind of computational tasks on the classical side. And similarly, I showed you by just showing one small example of how interference pattern which arises from the superpositions which we have, and the maybe some interplay between the phases, because in interference we always play with the phases. So I showed you that how phases and the interference pattern is very important in quantum algorithms, and especially giving an example of one of the important quantum algorithms which maybe you can read more about it. It's called a quantum amplitude amplification. So, and these were some of the ingredients which helps us to at least get a sense. Why is it that in quantum computing, they say there's a computational advantage, it's more powerful. What is it that we get on quantum computing side, which is not there on the classical side? I hope with these simple and maybe informal or maybe a little bit intermediate level technical discussions, I try to give you an idea why is it that quantum computing is more powerful than classical computing. But the story continues. Let's keep going. Okay, now we want to see, coming back to the question which Professor Shikha asked earlier during presentation, is what happens on the quantum qubit level? How big is this qubit as compared to the classical one? Okay, so yeah, to get a sense of that, let's say first we are at the 1 qubit state, okay, and then at the 2 qubit state, it's more or less similar. We have just 2 basis states, even though when I say qubit has just 2 basis states, please don't understand it is just the same thing as classical, which also has 2 states, like as 2 logical states. A qubit, even though it has a 2 basis states, there are many superimposer states which we can create. So the general state for a qubit is A times 0 state plus B times 1 state, and A and B are complex numbers. And maybe I don't know whether someone of you was asked kind of thinking about it. Okay, I did mention about the phase of the qubit, but where is this phase residing in the qubit? So the phase of the qubit resides over here in the complex numbers, because complex numbers can be represented always as some real number multiplied by some phase in its polar representation. The polar representation of a complex number is, you have a z is the complex number, and you have a real number, some modulus of some real number, multiplied by e raised power iota theta, which is the phase of the complex number. And those phases, that's how the phases come into the qubits also. A and beta are complex numbers, and that's how phases are entering. And if there's a phase difference, if the angle for the polar angle for A and B are not different, which means there is some sort of a phase difference between these 2 states. And it is that phase difference which we later on use to arrive at the quantum computing. Okay, that was about the phase, but let us take a look what happens as we keep on increasing the number of the qubits. Here we have 2 states. Let's keep going. We go to the 4. When we have 2 qubits, we go to the level 4. Okay, and now we go to the 3 qubits. We have 8 quantum states. Okay, so n, now we have 2 raised power n. Now, if you just have 10 qubits in your quantum system, which is easily available on IBM quantum computers nowadays publicly, so which means you will have 1024 states available to you. Okay, which means you can maybe deal with the system size, the matrix size. If you want to now do some sort of a algebra with matrices, implement some matrix calculations on quantum computers, you can realize the matrices of the dimension 1024. And if you go to 20, you get in lakhs. You go to 50. If you just have 50 qubits, 65 and 27. 127 is the number of qubits which we have reached in IBM quantum computer, and the number of states which is possible with 127 is this big. So this big number of states is accessible on IBM computer. That's where we are as of now. And if you keep going, and the time when you reach 275 qubits, which I think is not many years away from us, it will have more quantum states than all the atoms, the number of the atoms in the observable universe. So, and this is as of now, we are in 127, maybe a few years down the line, we will be at this stage. So this is the immensity of the logical space, which becomes available to us when we have qubits. So this is as you can see, is an exponential growth because it's 2 raised power n. So the state space of a quantum system or qubits or a quantum computer is exponentially bigger than the classical computer. In the classical computer, you just say you have 3 qubits, it's 2 raised 2 into 3 is 6 bits of information is available to you. While as in quantum qubits, it grows exponentially faster. Okay, so that is how big the quantum computer has in terms of the logical space, and that's why it becomes naturally. This is one of the reasons why quantum computers become more scalable. Okay, and now I wanted to talk a little bit slightly about the something called in terms of I mentioned, as we keep on making progress on these devices in terms of hardware, it is not just the number of the qubits which is important. So in IBM, we talk about scale, we talk about quality, and we talk about speed. Scale is just the number of qubits which you are kind of going ahead with, and in the scale, in the qubits, it's always that you would like to get high coherence. There is something called a coherence time associated with qubits. They should be highly reliable, and it should be a lower cost one. And if you look at the map in from 2020 to 22, the journey will be, we had just 65 qubits in 2020, and now we have 127 qubits, and we are on our journey to 433 qubits. And then there is something called quality. It is not just the, if you have many, typically we think, okay, if I have a larger number of qubits, it means effective, it means a good computing, but that's not the case, because the hardware is very noisy. So you have to find a way. And one of the measures of understanding what is the quality of your qubit is the quantum volume, which indicates like as quality of circuits and how faithfully circuits are implemented on your qubits. So, and in 2020, our quantum volume was 32, but as of now, it is 512. So, and we are definitely moving on our way to increase the quantum volume. Similarly, speed, the way you think, okay, you think of speed in flops on a classical computer, floating point operations which you do on a supercomputers. Similarly, on quantum computer, we have something similar, which is called circuit layer operations per second. It's like how many circuits are we running per second. And in that also you can see there is some progress, and we would like to increase the speed as well. Okay, and then I don't want to get into the details of what is happening. There was some news about it. What I want to do for the educational purposes, I just want to take, if there are some questions about the presentation, and then I can move to, I just wanted to show you some tutorial on the actual Qiskit. So Professor Shika, what should we do? Shall I go directly to the tutorial or take a questions first?
So we can ask if they have any queries. Any queries from the participants, please? Any queries? You may write in the chat.
No, I don't think so. In chat, yeah. I could not see it.
Yeah, please proceed.
Okay. So maybe I'll stop sharing the screen.
Yeah.
Just give me a moment. I will share my other screen.
Yeah, sure.
Okay, so I hope the screen is visible. Can you see this new screen?
Yes.
Multiple qubits.
Yeah.
Okay, good. So this, what I wanted to do is, I talked about entanglement. We talked about mathematically about entanglement and all that, but I just wanted to take a minute and walk you through how do you implement. Okay, if you have access to the IBM quantum computers, which you have, so, and you can easily set up that access. You have to just Google on IBM quantum experience and you can set up that access. So what we want to do is, in terms of Qiskit, I want to implement this quantum circuit. How do I do that? And I just want to show you that code. You see over here, what we are doing is we are just importing from Qiskit. From Qiskit, you import something called a quantum circuit, which is the basic primitive, and then air, and then ensemble. So, and then we also need NumPy, which is the library for doing matrix computations and some visualizations. Okay. Now, how do you implement whatever? Let's say I was saying, okay, I want to construct. First of all, I want to make a system which has 3 qubits in it. How do I do that? So I write quantum circuit, and then I write the number of qubits which I want to take. So I just want to have a system with 3 qubits. So I will say quantum circuit, then in parentheses, I write 3, and I just give, this becomes a quantum object, which I want to save, I call it QC. Then what I want to do on each qubit, I want to apply a Hadamard gate. How do I do that? There are two ways to do it. Either I write QC dot H, then I say the qubit number 0, 1, 2. That's the indexing, Python indexing. So you say QC dot H0, QC dot H1, QC dot H2. But that's not the good way to do it because I have to do it individually. Rather, why don't I basically create a loop for it? So I create a Python for loop. I say for qubit in range 3, QC dot H qubit. So whatever qubit it is there, we have a range 3. So it will apply a Hadamard gate to each qubit. And then what I do is that we say case QC, it has a draw function, and draw uses maybe matplotlib, and then it plots these qubits. Fine. So you can over here in line, you can run these, like as you can just run these, the code, and it will be, this job will be sent to the computer and it will get run. Okay, you can try doing that as well. So okay, so this is the way. So I think this small block of code, it helps you to create a system which has 3 qubits. Then you have that helps you to get the quantum circuit. And on the quantum circuit, not only will you be able to create the qubits, but you can also apply quantum gates, because a quantum circuit has qubits, then it also has the quantum gates. So this is the first thing. And what will happen, as I told you, that when you apply Hadamard gate, what it does, it puts the 3 qubit states. We would have initialized them in a 0, 0 state, but after we apply Hadamard, they get into superposition. We will be now in a superposition state, and that superposition state is represented this way. We call it plus 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 state. Okay, now this is the state of the system after we applied 3 Hadamards. Okay, now what we want to do, we want to say, okay, as of now, we just created this quantum circuit. We did not.
I have one question. Like we created the 3 circuits, and like we are applying these Hadamard gates in the order, in sequence, or what? Like from Q0 to Q1, then Q1 to Q2. Is it an order, or the on the different qubits we are applying these Hadamard gates?
Okay.
Like Q0, Q1, and Q2 all are 3 separate qubits, right?
Yes. So what is happening? We have just created, this is one single, this whole thing which you are seeing over here.
Yeah.
This looks like disjoint. It looks like separate from each other, but
Right.
This is one single quantum circuit. It's one single quantum circuit. And in this quantum circuit, we have 3 qubits indexed as Q0, Q1, and Q2. And what is being done is on each qubit, we are applying a Hadamard, which looks to you horizontally. It's like, because it's a quantum circuit, it has a horizontal direction. I'm sorry, it's like one layer. It's a vertical, not horizontal. These 3 Hadamards are applied vertically to 3 qubits. Okay. So which means following, like as the earlier state, our quantum circuit was in some initial state. Typically, it is 0, 0, 0. All the qubits are in a 0, 0 state. After the Hadamard, they get in a different mixed state, which is, we call it in Qiskit, it is represented like this. Okay, now what is to be noted is that we have just created this quantum circuit. We have not run this quantum circuit anywhere. So if we want to run it, that is the second piece. One is like creating a quantum circuit, taking the number of qubits whichever you want. Let's say you can take 5, 10, whatever is needed for your quantum algorithm. And then you create the quantum circuit, apply quantum gates, and finally do the measurement. After that, we also have to run this quantum circuit. That's another piece of it. And running, what do we mean by running? So you have to take, you remember I imported the air over here. So air, so we say, okay, what I want to do is, first of all, take something called a backend. Backend is, it can be a simulator or it can be a device. So we have to specify where do I want to run my quantum program. So in this line, we have specified that we want to run this program on something called air simulator.
So how do I decide which one I am supposed to use?
Okay, so we have typically a choice. We have many simulators, and I think air is one of the best among them in terms of the performance and the speed and all that. Maybe the first to go, maybe the default one should be the air simulator. But sometimes what you want to do, you want to say, okay, I want to run this quantum circuit, and finally I want to get access to my state. What was the final state of the quantum circuit? Then you have this option of something called a state vector simulator. Okay, so
Okay.
if you just type, maybe you can just explore it, the Qiskit simulators, available simulators, and it's available on our website, Qiskit website. So there's a choice of them, like a state vector simulator, chasm simulator is there, air simulator is there, and then there's a some more other simulators. So it depends on what do you want to do. Do you want to look at the state? Do you want to look at the, and there is something called a quantum simulator, which gives you access to the final probabilities of them after you do the measurements. So you want to look at the histogram of the probabilities or something different. It's up to your need. What do you want to do? We have a choice of simulators available. Okay, so then after that, what do we do is from the quantum QC, this is just, we say, okay, we just select some simulator, the backend, whatever backend we have. And after that, you say, okay, this is just for saving the state vector. Now we have the quantum object. Our quantum object, as I said, is our quantum circuit, and we have to, this quantum circuit needs to be some sort, we need to just assemble it. We just assemble it, and then we create this Q object, and then finally we have to run it. That's where it is happening. From the air backend, the air simulator, we say it has a function called run. So SV sim, we say there's a dot run, and dot run is, as you are familiar, it's a Python kind of a syntax. You call that function, pass it on Q object, and then you can, I mean, we are doing many things together in one single line. You can separate them. You can first do SV sim dot run Q object, save that first. Then after that, you can extract results from that, and finally you get state vector. But we are using this functionality in Python. We're doing all of them together in one single line. So what is happening? First, the object is run, then the results are extracted, and then from those results, state vector is being extracted. And then you can do a visualization. You can take the visualization, you can take the array, the state vector is an array, it can be rendered into the LaTeX. That's more of a visualization. But this is how you start. You define your quantum circuit, apply the quantum gates, all the quantum gates which you want to apply, and then take one of the, define your backend, whatever backend.
I have a question, that does it take so much time to execute that, like you started the execution in the beginning and now still it is executing?
No, this is, no, if I have to execute, I have to go into something called IBM Quantum Experience.
Okay.
And I wanted to ask, so do students know about IBM Quantum Experience?
Yeah.
So what we have,
Mr. Sanjay shared that.
Okay, because see, that is publicly available. I would say for learning or for even doing research, one should create account with IBM Quantum Experience, and all the publicly accessible resources are there. There are lots of tutorials which show code wise what you can do, lots of examples. What I'm showing now is it's actually a textbook. It's from, as you can see over his textbook.
Okay.
So I just wanted to show you example.
Yeah, okay, fine.
Okay, so this was, I think this part, this piece is clear. And then you can see, okay, if you want to apply some other gates, earlier we applied just Hadamard. Now, if you want to apply poly X, and we have poly X, we have poly Z, Y, and poly Z. And the notation is very simple. You just name it. You say QC dot X, then you specify on which qubit you want to apply that particular gate. Like as we have said, just create a small quantum circuit of 2 qubits, apply Hadamard to the first qubit, which is the qubit 0, and apply the X gate, poly X, to the qubit second qubit, but it's qubit 1 in the notation, and then you draw them. Fine, and that's what you get. Similarly, you can do many more things. You can, whatever gate you want to do. So here, earlier you had a question about, we are still using air simulator, but within the air simulator, sometimes you want to say, okay, what was the final matrix? All these gates I have applied. Every quantum gate is a unitary matrix. That's an interesting thing about quantum gates. They are always unitary gates, and you want to see what was the final unitary which I have combined using all these gates together. So there's a function for that, which is like get underscore unitary, and it will give you access to the unitary as well. Like as you got access to the state vector early on by taking this function get state vector. So that's how it goes. I think similar. Sometimes you may say, you don't want to do anything to your qubit, which is the identity operation, and That's what we do. Like as we have not done anything to our first operation, no gate was applied. It's like that. It remains like this, and we have applied X gate to the second qubit. So now this is the interesting case. This is what I wanted to present actually. This is what I want to take to. So which is like we ask this question that there are one of the special states which we use in quantum computing are called the entangled gates, or called the entangled states. How do I create entangled states on a quantum computer? How do I write a program and create those states and do some interesting stuff, do some measurements or explore their properties? The way to do that is we will need two special gates for them. Hadamard is already there, but then we will need one more interesting gate, which is actually a two qubit gate. It's called the CNOT gate. What CNOT gate does, it first of all, as you know, in classically also, it's a control gate, and these control gates first look at the control bit, and then they do something to the target bit. Same logic is here also. In the control gates, they look at what is the state of the control qubit, then they do something on the target qubit. Okay, what do they do and what do they see? This is our input, which is our control, and the output is their target. Okay, if and C0 is applied on two qubits, which means we will have two states, 0, 0. Let's say the left side is our the first qubit. This is target, this is control. That's how the notation is. First one is this on the one from the right side is the control, and the other one is the target. So if the control bit is in 0 state, nothing happens to the target. If the control bit is control state is on 1, the another state, we apply a X gate, which do a NOT operation, which means it will get flipped. It gets from 0 to 1. Similarly, once again, nothing happens to 1, 0 state. It remains like this. The 1, 1 state, because the control qubit is in the 1 state, so the other state will be flipped. So it's only the two qubits, two states which are getting flipped. The rest 2 qubits remain same. So that is what C0 does. Okay, that is if you want to see it in terms of matrix, it looks like this. Okay, now what we want to do to create the entangled states, we first of all start with 2 qubit system, create a quantum circuit with just 2 qubits, then apply Hadamard to the first of them. Draw. Okay, we now have this particular system. Okay, after that, what we want to do, we want to apply CNOT gate, keeping the first qubit on which we applied Hadamard as the control, and the another qubit, which is the second one, as the target qubit. This small magical circuit, which has one Hadamard and one control NOT operation, does the magic. Because you will see after we have applied this, and if you do the measurement now, you will see our system will be in a state like this. It will be in 0, 0, and a combination of 0, 0 and 1, 1 state. And why is it entangled? Because if you try to decompose this state and try to write it as product of 2 individual states, you will see you will never be able to do that. Okay, in fact, this is one of the very special states in quantum computing. It's called the Bell state. Very, very important. One of the first examples of entangled states is called this. This is one of those Bell states. So this is the Bell state, and it's entangled state, which means once you have created it, and the way to create it is very simple. Go to your quantum, write a quantum program, which is actually written here. You create a quantum circuit, apply Hadamard to first, and then apply C0 to the second, and then you get to the 0, 0 state. Maybe today it's not possible today, but I can still give you a sense of why it's happening. Because what Hadamard does, it puts the first qubit in superposition, which means now the state on the first qubit is 0 plus 1 equal superposition, and after that, on that 0 and 1 state, we are just taking something called a tensor product. So this was in a superposed state. This is like 0 plus 1 state. Multiply this 0 plus 1 state with the qubit state 0 over here. It becomes 0, 0 and 1, 0. Okay. On top of that to input state, we apply CNOT gate, and CNOT gate will see what is the state on the control qubit, and accordingly it will act. And when it acts, it finally gives rise to this particular entangled state. And that is how you create your first entangled state, which is the Bell state, and you can do a lot of stuff. Two things I want to mention, which you can immediately do with entangled states, is called superdense coding and quantum teleportation. You don't need anything more than that. It's like you can just start with the Bell state and show and demonstrate on quantum computer that you can achieve. You can at least write quantum programmers to see superdense coding and quantum teleportation. Those are two important protocols that send information across between two people without any quantum channel. On the classical channel, they send information, but it helps you to achieve that power. And if you look at, if you do a measurement on Bell state, you will see the probabilities will be half for 0, 0 state and half for 1, 1 state. And that's how we create the entangled states. And this is the starting point of doing something very meaningful, very powerful on a quantum computer. Okay, so I think maybe more I will first stop here, and because this is what I wanted. This was my plan of walking you through through this tutorial.
Excuse me, sir.
Yes.
Can we have one Hadamard gate and two C0 gate? Suppose,
Interesting.
like in this case, we have taken one H and one C0, and then suppose we are taking one H and two C0, then what would be the result? I
Okay.
just want to see that.
Yeah, surely. This is interesting question. So with Hadamards, what will happen? So Hadamards have this interesting property. If you apply two Hadamards on the same qubit, if something very magical happens is they square to 1. Okay, which means if you apply two Hadamards, nothing happens because it becomes an identity gate. If you apply two Hadamards on the same qubit. So these are called, they have a name, these are called Clifford gates, and the Clifford gates have this property that if you bring two of them together, they square to 1, which means and bringing them together means actually a multiplication. You are multiplying them together because you can think of them as matrices also. So if you apply two Hadamards, you are multiplying them together, it will give you 1. Nothing happens if you bring two Hadamards together. So therefore,
okay,
the way to create entangled state Bell state is you can take Hadamard. However, what you can surely do is if you can shift this Hadamard, maybe you put some another operation, let's say poly X or poly Z or some other operation in front of Hadamard, then you will get a different state. Let's say if you want to ask this question, I want to get a different state, different Bell state, how do I do that? So you have to do something additional to, in addition to applying Hadamard and C0.
okay, sir.
Any more queries by the participants? Any more queries from the participants? I request everyone to switch on their cameras for a group pic. All are requested to switch on their cameras, please.
Okay, meanwhile, maybe I'll just stop sharing the screen.
Yes, please. Everyone, please switch on your cameras. Kindly switch on your cameras, please. Thank you so much. And we are very glad that we were able to connect with Dr. Ruksan, and he explained all the concepts in a very simplified manner, like qubits, all the new gates which are part of the quantum computing, then entanglement, superimposition, interference, and with examples as well as the demonstration. Thank you so much, Dr. Ruksan, for being here.
Thank you.
Thank you so much.
Thank you very much. Thank you very much.
And with this, we come to the end of day 6, both the sessions. Our next session is scheduled on Monday, 10 a.m. by Professor Anirban Patil.